I'll never live down that title, I think. Unfortunately, it's also the title given to Margaret Thatcher. Not a
Where do I put that?
Just press it here. As my daughter said, female, F-E, so iron lady. So it's not, it's kind of, all of us are iron ladies. Yeah. Okay. It's a great delight to have Mary talk to us today about quantum gravity in the era of gravitational wave astronomy, telling us how we should try to think of phenomenology when we do our very esoteric kinds of approaches to quantum gravity. Thank you very much.
Well, let me first say good morning to everyone, and thank you to Sumati and Valavan for... What am I supposed to do? It's on, I think.
I think you can put it a little closer to you.
Is that okay?
Yeah, I think, does that work?
Okay, let me start again. Good morning to everyone. And I would like to thank Sumati and Valavan for the invitation. It's a great pleasure to be here. And also I would like to thank the whole Institute for the hospitality that was provided to us. It was really absolutely great, so thank you very much. So I was given this task to say something the day after the banquet in the morning. So this is a bit challenging, so that's why I put this shirt which has bright colors so people can stay awake. So as you can see, I was asked to talk about gravitational waves and quantum gravity, but I'm going to talk about gravity in the era of gravitational waves. And sometimes there will be some notion about models which are inspired from quantum gravity. We're not there yet, you are not there yet, in order to see really effects of quantum gravity with gravitational waves. So there are really very strong affinities between quantum gravity and cosmology. As you know, as we heard during this week, there are questions in cosmology that they have and they are going to be resolved with quantum gravity, like the initial singularity. For instance, we have bouncing models, which came from string theory, LQC, GFC, that we were able to somehow to go beyond this initial singularity. Explain the early and late accelerated expansion of the universe. I'm not very fond of the inflation in the very kind of standard way that people see it. So to my mind, should be a kind of quantum effect. At any rate, this took place at very early stages. So quantum gravity could give or should give an answer to that. For instance, in group field theory, by trying to match together, to glue the quantum tetrahedral, let's say the blocks of geometry, we're able to find some dynamics that lead to exponential expansion. And as we heard the other day from Renata, there is also this let's say, plan to be able to find the homogeneity of the universe coming from quantum effects in the approach of CDT. In the same way, we would like to find the origin of initial perturbations coming from some quantum effect. And certainly, quantum gravity could explain the dimensionality of space-time. This has been seen. We have shown that in the case of string theory, and again in CDT, there was some approach to this question. On the other hand, I think that cosmology is the only hope in order to test quantum gravity. It's a real unrealistic dream to expect that we're going to have a lab at energies of about 10 to the 19 GeV. But we live within a lab, which is our universe, and we could use it in order to test approaches to quantum gravity. After all, a model should be accepted not only if it is consistent, not only is mathematically beautiful, but should explain the universe in which we live. So there are many ways through cosmology to test models of gravity, but today I will focus on gravitational waves. So here is what we know. Actually, what I'm going to say basically is what we did within the LIGO scientific collaboration, and on and off, I will give you some results of my own work outside of the collaboration, okay? But basically, I will review test of gravity within LIGO, Virgo, CAGRA collaboration. So here you can see all the events that we had at the end of the third observing run, which goes from the 1st of April 2019 to the 27th of March of 2020. Altogether, we have 90 events. And now the fourth observing run has started on the 24th of May and will go on for 20 months plus 2 months that will be commissioning. So we learned a lot of things. We learned about astrophysics. We learned about masses and spins of compact objects. We learned about the equation of state of neutron stars. We learned about cosmology, the problem with H naught. We can, by studying, the anisotropy that comes from the gravitational waves signature, we have an independent way of studying the large-scale structure completely decoupled from the electromagnetic spectrum. We study beyond the standard model particle physics, energy scales that cannot be reached at LHC, will not be reached by any terrestrial interferometer, and we have tests of gravity. So the different tests, so what I would like to do is to tell you what are the tests that we do and where we expect to have a difference if we have a theory beyond GR, and what the results that we have today. And then you pick up whatever test you want from your favorite kind of gravity model. So there are two tests that we do, the consistency test and the parameterized test. The consistency tests are the simplest one. You say GR is correct. I have the waveforms that come from GR. My free parameters are the astrophysical parameters, and then I try to see if what my data give matches these templates. And from there, I read the mass of the black hole, the spin, and so on. These are the simplest tests. The second one are the parameterized tests. Now, you are going to pick up some parameters which are going to model from your theory what kind of difference you have from the GR, and then you are going to constrain these parameters. Among the 90 detections that I gave before, we use 15 ones that they have a signal-to-noise ratio bigger than 6, and they have a false alarm ratio smaller than 10 to minus 3 per year. Usually in the collaboration, we're quite conservative.
Just a small question. So in the so when you detect or announce a detection, then don't you do template matching, and those templates are from GR, no?
They're from GR.
So I'm getting a little confused then. So when you say you are looking at known detections, which are known because you use GR.
No, I'm not saying using no detection. I'm saying that I have my template, which is from GR,
Yeah.
and then I'm going to match my data, what I observe, with the model that I have. And that within GR is going to tell me what are the mass, the spins, and whatever of my objects. And then there are as well waveforms that they are outside GR, or they have post-Newtonian corrections that I will talk.
Okay, maybe.
Okay, so you have a way to parameterize. I will talk about that, how you parameterize beyond GR, and there are waveforms that they take the spin, there are waveforms that they take that the mass of the graviton might be different than the spin. So there are ways of, to take into account in your waveforms what will be the signal that you
Even though the announcement of a detection is through GR templates.
It's through GR detection. So there are two types of tests, I said, the consistency test and the parameterized test. So let me start with the consistency test. These are the simplest one because you do not have any new parameters to put. You say GR is correct, and therefore I'm going to try to match exactly what I said now, my waveform that is given with the data that I have. And here you have two types of tests, the residual test and the in-spiral merger rig-down test. What is the residual? The residual test is going to try to pick up if you have some kind of difference between the waveform and the data. In other words, you do the best kind of fit between the waveform and the data. You remove that, which we call it a residual, and then what remains, it should be just noise. If it's not just noise, that means there is a signal which is beyond GR. Then you do the in-spiral merging ring-down test. What you do there, you are going to calculate the mass and the spin of your compact object, okay, by using only the in-spiral waveform or by taking as well the merger and the rig-down. If GR is correct, then the mass and the spin that you find should be the same. Why? Because if you go to the in-spiral phase, you are in the weak gravity regime, so you do not expect to have any kind of changes there. Now, what are the difficulties you have? If you go to the residual kind of approach, what it happens, it's often a bit difficult afterwards if you have a discrepancy to be able to model it, to find from where it comes. But these are the simplest tests which you do because you do not have to put any new parameters in your model. Okay? So this was done. I'm not going to, usually are statistical methods that people use. You do a Bayesian analysis and you try to see whether you find any kind of deviation between the noise when you have extracted the best fit and what are the masses and spin of your object once you use only the inspirer or you take the post-inspirer kind of events. And the result out of that was that there is full agreement with GR. The next test on which I will spend most time.
15 events.
Yes. You will use the 15 events because we have a false alarm ratio which is more conservative and signal to noise ratio bigger than 6. So then we move to the parameterized test. This is where I will spend more time. So here you introduce some parameters and you try through this parameter to capture a signature that will tell you that you are beyond GR. Here you are two types of tests, the inspiral and the ring tap. So in the inspiral, because you are in the weak regime, weak gravity regime, what you are going to use? Post-Newtonian approach. So you are going to write your waveform. You are going to have the amplitude and the phase. You are going to write the phase in terms of post-Newtonian parameters, which you are going to consider them to be completely independent. And for each of them, you are going to find what is the mass and what is the spin. Okay? Now, the difficulty that you have here is that if you find a discrepancy, then it might not be trivial to be able and to map from which theory it comes. And the second difficulty that you have, there are models beyond general relativity where it's not really very simple to write the phase in terms of post-Newtonian parameters. The second thing that you do is the ring down test. You try to construct parameterized ring down waveforms which are based on the perturbative approach of the ring down you know in general relativity. The difficulty that you have here is that it has been shown that spin can be an important constituent, and it's not very easy beyond GR to model rotating black holes. The second difficulty that you have is that you have to go in the ring down to calculate the quasi-normal modes, and really, technically, it's very difficult to do it beyond GRs. They are not the mathematical tools. This is not the corresponding Kolsky equation which exists in the case of GR. Now,
there's also the other issue, that namely, for the event so far, we have very few cycles in the quasi-normal.
Yes, but I'm saying in general. In general, that's what we do. Yeah, it's very difficult to do it. But there are approaches from numerical relativity to it. Now I would like to go to something that probably can be a bit more relevant to the quantum gravity stuff, I mean, whatever, is where do you expect to have a difference between GR and the different theory of gravity? In the generation of gravitational waves, the propagation, the polarization, and what will be the remnant. What I mean by generation? Well, the word says by itself. Is the outgoing radiation, which depends on the properties of the compact object, something which even in GR is not simple to be done. Propagation. The effects could be dispersion, birefringence, and amplitude damping. What do I mean by that? Okay, when you write, I give you some general way. When you have the dispersion relation, standard GR, E squared equal P squared C squared, P momentum, E energy. Now, for theories where you have Lorentz violation, which is generically within quantum gravity approaches, then you are going to have these extra terms. If you put A and alpha equal to 0, you have the standard massive gravity, okay? Then you have for double special relativity, you have this form. This is a parameter that depends on the Planck length. If you have extra dimension theories, you have these terms. This is the mass of the gravity, graviton, sorry. This is a parameter that depends on the square of the Planck length. Horava-Lipschitz theory, theories with no commutative geometries, and so on and so forth. So you have some changes in the dispersion relation, and I will tell you how we try to study them. Birefringence. There are quite some approaches like the Simon's gravity, ghost-free scalar tensor theories, symmetric teleparallel equivalence of GR, Horava-Lipschitz gravity, where the gravitational waves, as they come from the source to your observer, there is a different kind of, they are suppressed or expanded the left with respect to the right modes. In other words, you have parity violation. And we're looking for parity violation within the signature. Either from detections which are, like a collision of two objects, two compact objects, transient effects as we call them, or from the gravitational wave background. And I will mention where we are with that. And the last is the amplitude damping. So here I give you the perturbation equation, okay? H is the Hij is the tensor modes. I am in conformal time. This is the Hubble parameter in conformal time, the prime. A is the scale factor. This is I am in Fourier space. This is the speed of the gravitational waves. Mu is the mass. Gamma is anisotropic tensors. And this, where is that? This nu is the Planck mass run rate. In the case of GR, mu equal to 0, gamma equal to 0, CT equal to 1. If I am in the case that I have gravitons propagate at speed different than the speed of light, and if I take the simplest case with no anisotropic tensors, this is the strain of gravitational waves, and as you can see, there is this damping factor here, and this is a time delay that you get for the arrival of gravitational waves with respect to the speed of light. So here are the differences which you can have.
Yeah. So this does not is not directly related to the dispersion relations.
No, this is different. This is
so. For example, you could have something in which there is some intrinsic quantum gravity driven damping, and.
Yeah, whatever mechanism you want, that will be damping. Here I highlight how you could see it, and then I'll tell you what test we do. But first you have to model it, to map it, how different it will be. This is the simplest possible exam. As you can see, I do not have anisotropic stresses so that I can easily solve my equation. So that's what you can. Then I am in the polarization. As you know, any other theory could have, any metric theory could have up to 6 polarization modes, 2 scalar, 2 vector, 2 tensor ones. Something for me? Okay, so here, for instance, I give you schematically what will be the deformation of a ring of test particles, U plus, the cross, the 2 vector ones, and the longitudinal and breathing modes. So here I am in the xy plane. I have gravitational waves in the zeta direction, which comes perpendicular on my slide for the plus and cross and the longitudinal one, and for the other 3, it goes to the right of the slide. So you are looking for extra polarization modes. And finally, the remnant properties. We heard the other day about the equals. We heard the other day about the quasi-normal modes. So any kind of a theory of gravity beyond GR can give you a difference in generation, propagation, polarization, or remnant in one of them, in all of them, or whatever. So we're looking for them, and if we have a distinct kind of signature that something of that happens, then tell us that we have something beyond Einstein's theory of general relativity. So let me now start to going one by one and tell you what we do. So, test of gravitational wave generation. If you have a theory where you have higher curvature corrections, or you have some additional fields in your theory, then what you expect is that there are going to be some deviation of the energy and the momentum of your binary, and that is going to show in the gravitational wave signature that you are going to get. So I'm going, as I said, to remain now in the spiral. In the spiral, I'm going to use post-Newtonian approach. So here schematically you can see, so what I'm going to do, I'm going to expand in post-Newtonian orders, n post-Newtonian orders, V over C to the 2n, that means that I am in the n post-Newtonian order, and because there is a correspondency, if you use the Schwarzschild radius, that means Gm over R to the n post-Newtonian order. So here in this plot, for instance, as I go higher up, here I go to the strong field regime. As I go to the right, I go beyond linearized theory. So in this kind of gray kind of region, where I have that V over C is smaller than 1, of the order of the Schwarzschild radius over d, again smaller than 1, I am in the region where I can use a post-Newtonian approach. So this is the weak, slowly moving and weakly self-gravitating sources. So this is the regime of the inspirer where post-Newtonian approach is going to work. So what we do is I'm taking my waveform, okay? I am in Fourier space, and I am in the frequency domain. I write it in terms of the amplitude and in terms of the phase. And then I'm going to expand it in terms of post-Newtonian orders. So you have them here. So in other words, so here C as a subscript has to do with the time of the collision, denotes the collision. Eta is the asymmetric mass ratio of the compact object, and phi is defined in terms of, is defined in terms of the redshifted mass and the frequency. So we have this kind of parametric deviations of the GR. Each of them, each I corresponds to the I over 2 order of post-Newtonian expansion. And then you go to your data, and here I show the 90% upper bounds of the magnitude of these parametrized test coefficients, and you can see that the biggest kind of stronger constraint comes for the -1 post-Newtonian order, which is the phi -2, which is what we call the dipolar radiation, something that does not exist in GR, and it's nothing else than the momentum and the energy which is transferred from the binary to the additional fields that you can have in your theory. So as you can see, the stronger results that will come now is from the third observing run, this diamond. Now,
these parameters are assumed to be uncorrelated.
Uncorrelated, yeah, these are uncorrelated, yeah. So then I move to the dispersion.
Mairi, can you just go back to that slide? And
Yeah.
Can you explain exactly, I didn't get what these little diamonds are representing.
The diamonds corresponds to the different observing runs and the data we have. So the third observing run is the diamond, the full diamond blue. The full diamond gray is the second observing run, and the open diamond is the third observing run. So of course, as you have more runs and more data, this thing becomes more. And then the horizontal lines are from distinct events with a mass that goes from the blue to the red as you go from lower to higher mass compact objects. You're welcome. So then we go to the dispersion. Okay, as I said before, the dispersion relation is GR is square equal P square C square. For instance, if you go to massive gravity, you are going to have this extra term, okay? Then you are going to define what's going to be your group velocity, Vg, and then I'm going to compare. So here, to do this test, I need the electromagnetic counterpart, and I'm going to compare the time of the arrival of the signal, of the gravitational waves, and the photons that I get. For instance, an example, if I have a supernova which was at a distance d, then that's what is the relation between the distance d and the delay of the time with the group velocity, and then that will lead, with respect to where is the location, the redshift of the source, to a time difference of the two signals. So what we did in the collaboration, we used a phenomenological approach. So we're going to say, let me add an extra term where I have two free parameters, capital A and small alpha. And this, they take different values for the case of a theory that you have in mind. If, for instance, you put alpha equal to 0 and A equal to 0, you have just massive gravity. And then, for instance, 2.5 is multifractal space-time, 3 is double spatial relativity, 4 is Horava ellipsis and extra dimension, and so on. So you can find what is the corresponding dispersion relation that will come from your theory. For instance, with a colleague now, we try to find what the dispersion will be for non-commutative geometry and see what we can do there. It's not some, you have to put it into that form, which is not always simple, but that's something that you can do. And if you do that, then we have the way to make the constraints. So here is the group velocity, which is related with this dispersion relation. Then you have the scale of modification to the Newtonian potential. For instance, for alpha equal to 0, just the Yukawa potential. And then your waveform is going to be changed in the phase. The phase is going to pick up an extra term, and as the wave propagates from the source to you, this is going to become bigger and bigger and bigger. So then you go and you can make the comparison with your data. So here, I don't want to go into any details, but just in order to tell you that there are some equations behind all that, then we know how to write the correction to the term, okay? So you have to calculate that for your objects. We know it, how it is, blah, blah. So we did that, and then the constraints that we put in this parameter A alpha for different values of alpha, they are given here. So if you have your favorite quantum gravity model, that it will give you the correction to the dispersion relation, and you can write it in terms of this phenomenological way that I showed before, then you can go, and from this plot, you can read the constraints that there will be for your model. The stringiest constraint that came here is the constraint from the mass of the graviton, which is smaller than 10 to the minus 23, which is about 2 times stronger than the one that was the most recent one from the solar system bound. So then the question is, okay, how can I use that? So I'll give you an example how you can use that. The example will be for the case of massive gravity. So there were many attempts to create a massive spin-2 gravity, which is ghost-free. There was a problem because these models were usually pathological because of the existence of ghosts. That was done by that paper in 2011 here, and you have a ghost-free theory of massive gravity by introducing the Stuckelberg fields, and this was motivated from extra dimension and brainwards. Now, this model was very good in terms of not being pathological, but I could not do cosmology with that. Why? Because I could not find stable FLRW solutions, so forget it. And then it was proposed that it could lead to stable FLRW solutions if I add tensor or scalar modes. So I'm going then, as an example, to concentrate to the quasi-dilaton massive gravity. So it's an extension of the ghost-free theory of massive gravity, where it was introduced a quasi-scalar field. So my action looks like that. G is the dynamical metric, phi is the fiducial metric, and sigma is this quasi-dilaton. And from the interactions that you have between the two metrics and your scalar field, that's how you give mass to the graviton. So then we said, well, we have detection of gravitational waves. Can we do a test of that? So the first thing that we tried to test with a student of mine now for years back, whatever, was to estimate the decay probability of helicity 2 to helicity 0 from tensor to the scalar mode. And what we found was really very small. It's not going to give any kind of effect in the gravitational wave signature. And that is in agreement of what was already seen in the case of higher derivative corrections to the Hordesky effective field theory. And then we said, okay, let us try to do some kind of astrophysics to that. In other words, I have rotation curves, and I can go to calculate the gravitational lensing in that theory. I just repeat what was done for the standard GR. And then we found that the theory is safe if the mass is more than 10 to the minus 31 electrovolts. So it's safe. It's safe, but to my mind, it's useless. I mean, I'm sorry, I'm recorded and I should be a bit more politically correct. But a model like that you have the screening mechanism, you have all these things, and therefore it evades all possible kind of constraints, becomes of little of any physical interest. And that is the most polite brown line I wrote there. Yes?
I have a question. I'm not so familiar with these models of massive gravity, but isn't there a VDVZ discontinuity? Is there not a VDVZ discontinuity that occurs in these models because the mass of the graviton introduces additional propagating modes, and therefore just the constant in front of the gravitational law changes? I thought I'm just referring to this VDVZ discontinuity, which is if you add a mass to the graviton, you would change the shape of just planetary orbits because there's an additional propagating mode.
I think that is again below detectability.
It's a discontinuity. So even in the limit where you take m to 0, it's
yeah,
because there's an additional mode that gets produced.
I don't.
So this is related to the ghost freeness That's exactly what the DRGT removes.
I see. So it removes the VDVZ discontinuities.
Yes,
Yeah.
that's what's meant by ghost-free.
This model is beyond this model that I showed before is not only beyond ghost, but it as well plus another field.
I see. So this
Is the ghost free with the addition of a dilaton, quasi-dilaton field.
I see. So this is would not be Pauli Fear's gravity.
No.
It's not going to,
Okay.
It's
no.
a non-linear completion.
Fine. Okay. And the number of propagating modes is still 2, or it's more than 2 for the graviton?
it's 2 here.
It's just 2
It's two
modes
here.
for the
It's two.
graviton.
But you are good, yeah.
I see. Okay. Thank you. Yeah, I should understand better later.
So then I'm going to, remember I said I'm going to discuss about parity violation, okay? So I will give you an example about parity violation. So if you consider effective field theory, then if you have the leading order modifications to the Einstein-Hilbert action will come with either with 3 derivatives and mass dimension of 5, which means that the action can be written into that form. And these 2 terms where I have the 3 derivatives is where I will get the signature of the parity violation, where C1 and C2 are 2 functions, arbitrary functions of time, and MPV is the scale at which the parity violation is going to show up, okay? So here is, with respect to the left and right modes of the GR, this is the modification which we are going to get if you have parity violation, okay? And here I just write the relation between the cross and the plus modes. So then you can go and write down what will be the phase modification in the waveform, which is given here, in terms of the parameters C1 and C2 that you have to read from your particular model. And you go then to put constraints on the energy scale at which the parity violation shows, right? So that's what you can do. So here you can see that this correction that you have is to the frequency square, which is a correction at the 5.5 post-Newtonian limit. So then there has been a study by this person and collaborators here where they are trying to take all the transient events from the LIGO-Virgo-Kager collaboration detection and put a constraint, an upper limit constraint on the scale at which these parity violations will show up. So then you take your favorite model and you can do the analogous thing and you can find what constraint you could put there. Okay? Now, as I said, there is a corresponding kind of study that you can do, not by taking the transient, in other words, each of the CBC mergers, but by taking the gravitational wave background. So here, because I'm not talking to an audience that probably knows much about all that, I'm going to define, here I do, just for your own interest, a classification of the gravitational wave signature, the sources from where they come, and the way that you detect them. So depending where the sources remain during the whole observation in your detector or not, you call them transient or persistent. The fact that you don't know the origin, do you treat deterministically the signal or not? That is, you have phase coherent or incoherent sources. And then, for instance, transient phase coherents are the ones from compact binaries. Phase coherent and persistent are the ones that you take the continuous from spinning neutron stars. And then if you have the last case here, which are persistent and phase incoherent, is the gravitational wave background, is what corresponds to the electromagnetic, to the CMB. So here, this at the beginning, people thought that has an origin, cosmological origin, phase transitions, inflation, topological defects. That's why they expressed it in terms of a cosmological parameter, like always, omega GW, which is the energy density of gravitational waves in a logarithmic interval of frequency and normalized by the critical energy density. In addition to this cosmological background, there is a superposition of gravitational waves from astrophysical sources which are very far and very weak, and therefore you cannot detect where they come from. Like if you go to a concert that you don't know who plays the cello and where it comes the piano, whatever. And so we have this stochastic gravitational wave background. So in order to study the gravitational wave background, actually is an abuse of terminology to call it stochastic. If it's gravitation, it's stochastic. If astrophysical is not stochastic, but that's another story. So the signal that you get, the strain has the signal has the strain and the noise. The noise is very big. So actually, there is no chance to find it by itself unless you correlate the outcome of two detectors under the assumption that the two detectors have uncorrelated noise. So then what you do, you are going to write the strain of the right and left modes. Here it is written in terms of the omega, the parameter I gave before. And here, if you have parity violation, you have the right and left modes, is given in terms of this I and V, which are the stock parameters. So you build your two-point correlator. I'm not going to go into details. And then the omega GW has a contribution which comes from this kind of parity violation. And then we looked for a signature of parity violation in the stochastic gravitational wave background, and we found no evidence for parity violation within the O3 data.
This theoretical, or the last transparency here, the theoretical calculations you're showing up, they're all done in post-Newtonian?
No, the previous one, yes. Here you don't need it because it's the stochastic background. You don't need to go to post-Newtonian. It's just you know.
But there must be some approximation. So what is just linear?
The approximation I take is what I wrote here. I don't know if I wrote it. I didn't write. Okay. So I take it to be unpolarized. Here is before it was unpolarized. Here is going to be polarized, stationary, and Gaussian. These are the assumptions that I make. Okay, these are the assumptions.
So we don't care about don't systematically derive it because we don't know the. Okay, I understand.
There are models for which you have to go beyond this Gaussianity, and these they have been studied. For instance, if you have topological defects or phase transitions, will go beyond that. So there are corrections, but basically that is for astrophysical origin. So then Gaussian could be.
But then in the frequency range here, all those effects be most important?
Yes. But if you have the stochastic background I speak now, you are going to take the integral over all frequencies. Okay. Otherwise, if the individual, then you have depended on the frequency band, and the best frequency that this is done is about 25 hertz.
I see. So this is a strong band because even integral on the whole.
Yeah, you integrate over the whole thing. And actually, I don't want to go into details here, but we did it for different models that can lead to parity violation. For instance, Saint-Simon's gravity. Then we did it for axion inflation, and we did it as well for magnetohydrodynamic, I can never say this word, turbulence. So we did different cases that can lead to parity. Sometimes depends on the frequency, sometimes not. But I don't, I just highlight the basic results we have there.
What is O3?
Sorry?
O3.
The third observing run. I put that right in my first slide.
I'm sorry, I
should
have been there.
No, the third observing run. So all the data that we have now, the data which are public, they end with the third observing run. Now we're in the fourth one. We don't have any public data to.
And how long does the one run last? Like, is there a fixed?
I said that as well before. 20 months plus 2 months of commissioning. This is the effect of the day after the banquet or whatever. Okay. So then I want to discuss, remember I said for the propagation I have three things. I have the dispersion, the parity violation, and I have as well the amplitude damping. Okay? So there has been constraints. So this that I'm saying again now is for the case that I have an electromagnetic counterpart. And as you know, we had just one. We have the GW170817, which was followed 1.7 seconds afterwards by gamma ray observation, and that is the signature that we can compare between the arrival time of the two signals, taking into account. I'm not going to that, but it's obvious, taking into account as well the separation between the detectors. So, okay, constraints on the number of space-time dimensions from the gravitational waves. Okay, so if you have extra dimensions, then it's going to be some kind of leakage to the extra dimensions, which. Large extra dimension. So that means that the strain is going to go 1 over the luminosity distance, okay, to a power gamma, which depends on the dimensionality of the space-time. In addition, if the model is a bit more complicated and you have this screening radius and so on, then the relation between the strain as you read it from your gravitational wave interferometer and as it was given from the standard sirens, from your electromagnetic counterpart, it has this relation here, which depends on what is this n, what is this d, so the d is the dimensionality of space-time. The n, again, is a parameter that depends on your extra dimensional model, and RC is the screening radius. So this was done then from one event for different values of RC. You can see here the shaded are the excluded regions for different space-time dimensionality. And that already from the one event, we found consistency with GR in 4 dimensions, and some models, like the DGP model, is ruled out. So I found it quite amazing that with one event, I can rule out models. Yes? I don't have a mic. I have mine if you want.
Is the DGP model completely ruled out? There's no remaining parameter space? Or?
As far as I know, no, but you know very well that we are always able to put epicycles and add something new to make it, to revive it. So in that sense, you know, but then,
okay.
Yeah.
Just,
it's a matter of taste how many parameters you want to put. You put many, you have an elephant, I don't know. So to me, if the stand, you know, if the, let's say the vanilla model is ruled out, if I put more things to make it, it's not. But I'm sure that if you ask the authors, they will tell you that yes.
But here it's a question of the scale of.
Here is this
of the dimension.
Yes,
right? The extra
and the dimensionality. Yeah. So, I mean, with the parameters of the model, it is ruled out. You know, I have a scale between 1 megaparsec and 20 megaparsec, and you can see that there are the dimensionality of space-time cannot be above 4.
At the megaparsec scale?
Yes.
Okay, thanks.
With these values of RC that I give, yeah. Okay. So let me go to something else now. Again, putting constraints from I'm still in the case that I need an electromagnetic counterpart. So I consider models with dimensional flow, which are the things that often appear in quantum gravity, if I'm not wrong. So here I write down my perturbed action. If you have a small perturbation, H. So here is my source, and here is my kinetic term, okay? And these effects, this distortion of your space-time, are characterized in terms of this where it is rho, which is the space-time measure, and this kinetic term. And gamma is related to the Hausdorff dimension and the spectral dimension. So then, if I have that, I'm going to solve it and find what is the strain. And it's very simple to find that the strain, the gravitational wave amplitude, is given by the convolution of this J, which is the source, with a retarded green function, which actually depend on what will be your source. And then, if you are in the local wave zone, in any regime for which this gamma is constant, you find that the strain, the amplitude of the gravitational wave, is given by a very simple kind of expression, is the product of a dimensionless function, f, which depends on what is your source, and of this power law distance behavior. Okay? So then I have that for the plateau of the dimension flow, this is the expression that will relate the strain from your detector to the luminosity distance, which I will have to write it in all possible scales. And you can, because there is a multi-scale system, you can write approximatively that the relation, which is the corresponding of what I wrote before for the case of extra dimension, it is given here, okay? If I have one scale in my model, then this L star is of the order of the Planck scale, and this gamma is the UV. UV is the scale at which quantum gravity corrections have to be taken into account. Mesoscopic scale is the one for which quantum gravity corrections start becoming important. And then if you have this scale, then this equation is valid only near the infrared regime. So then I can go and I can constrain this ratio. By constraining this ratio from the data which I'm going to have, I can go and put constraints on the parameters of the theory, which is the scale, the fundamental scale L star, and this parameter gamma. So what we have, then I go to my to the literature, and for all the zoo of the different quantum gravity proposals, I can read what the value of this gamma scale is. And then we took the one LIGO event and simulated LISA events, which will be in the millihertz rate, and we found that the only way that we can put constraints by studying electromagnetic counterpart and gravitational waves if these conditions is satisfied. And if you go to read the table I gave you before, that could be GFT, spin forms, or LQG. Now, just let me finish. The disclaimer that I make out of that, I'm not saying that this one of these three theories is the correct quantum gravity. They can be right, they can be wrong, that's not the question. I'm saying that only one of these three theories can be tested with this way with electromagnetic counterparts. No, that does not mean that one of them is the right one. They might be not. So I would like to make this disclaimer out from the beginning. Yes? It was exactly that. Yeah. So then I would like to move to another test we did if I do not have electromagnetic counterpart. Yeah, if I don't have electromagnetic counterpart, because that might be the case. And then we said the propagation speed of gravitational waves can change with the energy scale. This can be done, for instance, in the theories that I just discussed. Spectral dimension space-time changes with the Probst scale. In brain-wave models, massive graviton, Hordensky theories, any of these theories gives that the speed of gravitational waves depends on the energy scale. Then I'm saying that if I take such a theory and at the UV completion of this theory, it has to be Lorentz invariant, that means that somehow, at some point, the gravitons propagate at the speed of light. But I have one event, the event I told you before, the GW17 or H17, which tells me that I cannot go very far away from the luminal velocity. So I'm saying that means, can I make constraints to a theory that predicts that the gravitational waves propagate at a speed which depends on the energy in a way that I am within the LIGO constraint at the kilohertz range of LIGO, and I could be away from that at the millihertz rate of LISA. So that was the question we did with some colleagues that I don't. So here we say, okay, let us write down the quadratic action for the linearized transverse traceless gravitational wave modes. So here you see this parameter. This is actually the propagation of the speed of gravity. So I would like. Then we took two ansatz, and polynomial ansatz. I'm not going into details why we picked them, but we can discuss it which. And the EFT-inspired kind of ansatz, where I have two parameters. Okay, so you can see I have a very sharp change. They propagate at the speed of light and propagate at speed which is much smaller, which depends on the frequency. So I have two scales, the scale at which it becomes this kind of transition, and what was the velocity away from the speed of light, okay? So this here, the speed of light depends only on frequency. We have done as well the version that depends on frequency and the redshift. It's much more complicated. I'm not going to show, it's full of equations. I just don't show any of that. And then the question is, can LISA put constraints to the GR parameters, to the astrophysical parameters, as well as to the free parameters of the model that will give me this kind of frequency dependence of speed of light. So to make the long story short, because time runs, here are the equations in post-Newtonian order that we did. I'm not going into detail. I'm not going to detail of how you, but I'm just, the end of that story is what I write here, that we have shown that with a big range of population of masses, LISA will be able to put constraints on the GR parameters and the free parameters of the theory. So now you can give me your preferred model. You can where I have this frequency dependence, how this frequency dependence of the propagation of gravitos is expressed, and then I can go and run my tools and see what constraints I can put and how they can be mapped to the parameters of the theory. So this, to my mind, it's pretty powerful because it doesn't need electromagnetic counterpart.
These calculations is independent of the frequency range of LIGO, right?
No, it's independent. No.
So
Yeah, this is completely. We're not using it because we have to go to the millihertz rates in order to do it. For LIGO, they obey LIGO. So we have the whole spec. But the study, the study was completely theoretical, but at some point we plugged values random to see what we can get. So now the polarizations, I have to go fast. I told you that there is as well polarizations. So the point is that it's hopeless to find a signature beyond GR in polarizations with just the 3 interferometers we have, because the 2 LIGOs have the same orientations, and I need at least 6 detectors to find the polarization. So there are some techniques. One technique is to constrain, I will just highlight what it is, this null stream. But in order to do that, and I will say what the null stream is, in order to do that, you need to know exactly where is the position of your gravitational wave. So you need to have electromagnetic coupling. And the second is something that we have proposed from the gravitational wave background. So what you do? So let me say that the strain that I get from my detector, it has all these kind of terms, where F, as you can see, are the angular pattern functions, which depends on the polarization, and against I have the waveform polarization here, the cross, the plus, the 2 scalar, and the vector ones. So the null stream is a technique that people use in the data analysis. Parenthesis, I don't do data analysis, so don't ask me too much about what they do. But they create these null streams. In other words, they combine the data of their detector to have a linear combination which has no signal, has only noise. And then this method has been then tried to be applied by here, these authors, to be used in order to create a null stream, in other words, to linearly combine through a projection of your data in a way that you are going not to have any kind of signal. So, because I cannot explain it in words, here it is. So here is my data. My data is split it in this term and the noise. So this term is the projection of your waveform, of your wave vector along all the possible directions which you can have, okay? And I have the plus, the cross, all the directions that you can have. So you construct a new databases where you do not have a GR signal. And then you use that to see if I have a signal, then that means that it's beyond GR. So this has been done, +5. The other things which we did, but again, probably because of the lack of time, I'll go very fast, because I like the stochastic gravitational wave background, so basically we work with that. So what we did is we say, okay, let us have so I'm right the 2-point correlation of my detector, of 2 detectors, and going back to Abai's question is because I get Gaussian statistics, the 2-point correlator is sufficient. So I write it in terms of these quantities, which are geometrical quantities about the position of my detector. And this H function here, which encodes the spectral shape of the gravitational wave background and is related to the cosmological parameter for the gravitational waves, like that. Then we said this omega, so in other words, the energy density of gravitational waves in my universe is going to have 3 kinds of components. One from the tensor modes, one from the vector modes, one from the scalar modes. The parameter here, for people who don't know, if I was taking the gravitational wave background from compact binaries, it goes like f to the 2/3. You write down the quadruple formula. If you have the case of inflation, it's a flat spectrum. If you have phase transition, it is a broken power spectrum. Okay? So then, if I have scalar vector tensor modes, we are going to have different kind of values here, different values of this exponent. And then we propose a Bayesian analysis. We have the signal with all possible signals that you might have, like a tensor vector scalar or a combination versus noise. And then the GR versus not GR, so I have tensor or I have combination of all of them. This has been applied, has been always applied from the time we proposed that in 2017 up to now in the data, and there is full agreement with GR. They are not extra polarization modes, as you can see here. It's consistent with the pure tensorial analysis. Now, the ring down, yes.
Just before you move on, these constraints only apply if the additional modes or the additional polarizations propagate also with the speed of light, right?
Yes, here we cannot, yes. Yeah.
Okay.
We consider that there is speed of light, yeah.
Thanks.
Because, if you change many of the things, you don't know where it comes from. The ring down, it was mentioned, I think, 3 days ago, that, okay, what you expect is that at the end of the coalescence of the two objects, you are going to get a perturbed Kerr black hole, which is going finally to reach a stationary state by emitting gravitational waves in these quasi-normal modes. And if you take the no-Kerr conjecture of the GR, then the frequency and the damping time of these gravitational waves should depend only on the mass and the dimensional spin. So here is the expression which you are going to get from the ring down. And this null hypothesis has been also tested in the from the collaboration, and was found that there is really a 90% kind of agreement with the no-Kerr conjecture in GR. I'm not going to go through that because it was mentioned about ECOS. ECOS have been as well searched for. There is nothing for ECOS. So let me move to something else very fast. I would like to think about pulsars, because people might have heard that over summer there were individual announcements from the European PTA pulsar timing array, from the nanograph in the US, from the Indian one in PTA, from the Australian PPTA, and I think I did the tour of all of them. Right? There is no, these are separate collaborations. I'm not part of these ones, so I'm telling you what I hear. So it will take them about a year to combine all the results and come up with the full kind of collaboration. Now, what is interesting here, we go to the nanohertz range, okay? So this pulsar timing arrays, therefore, if you take theories beyond GR, in the post-Newtonian order, the effect that you might have could be dipole radiation in scalar tensor theories a -1 post-Newtonian order, extra dimensions or time-varying Newton constants at -4 p.m. So why I say that here is interesting, because we are in even lower energy scales, frequencies, because lower frequency means longer wavelength, means wider orbits and heavier optics. So therefore, with these PTA experiments, the objects remain much more during the inspiral phase, and therefore you would expect that probably they can give post-Newtonian order corrections more important than the ones that we have with terrestrial interferometers. There has been somehow it's not fully, declaration that the gravitational wave background of astrophysical origin has been so defined, but there are very high hints that probably the collaboration has found it. And because I would like to make also a kind of advertisement of some very old work of mine with a student, my first student that I knew as postdoc afterwards. I'm going to tell you about constraints that we put ages ago by studying pulsars in non-commutative geometry. So we took the model of Alain Con's, which is the non-commutative geometry spectral action, which tells you that if you want to take very seriously the interaction between matter and gravity, then he proposes that space-time is the product of a four-dimensional Riemannian manifold M and a discrete internal space F of 2 points, which is not commutative. Then if you pick up appropriately, this internal space is defined by the choice of an algebra, a Hilbert space, and a Dirac operator. And if you take them in an appropriate way, particularly the algebra, you can find the standard model, the most successful Heinz physics model we have at hand. How you do physics with that? You have to write the action. He proposes to use the spectral action principle, where the action is just given by the trace of the eigenvalues of the Dirac operator normalized by this value lambda, which is the scale at which the theory works. You are going to expand that by heat kernel methods in terms of these silly DeWitt coefficients. And then you can roll and right now the gravitational part of this action. I do cosmology, I care only for that. So here there are three free parameters which appear, which the A0, which comes before in front of this Weil tensor kind of part. Here is I have no minimal coupling between the Higgs and the Ricci. So here, this is the alpha 0 has to do with the coupling constants at unification. So I take this model, is a complex kind of study to go and calculate the tensor perturbations. Okay, so I calculate the tensor perturbations. And then I'm saying, okay, I calculate the tensor perturbations here, and I'm going to consider the quadruple formula in order to achieve the emissions of gravitational waves. And what we see is, and then I take at the time, that is very old actually, it's more than 10 years ago, this thing. So what we did at the time, we took the pulsars that they were at hand at the time. We calculate what will be we know the orbital period, we calculate the emission of gravitational waves, and then we can see that we can put a constraint because what we find from this model would be within the kind of accuracy of the GR prediction. And by doing that, we're able to put a constraint on this parameter, which is the parameter that has to do with the couplings at unification. Later on, let me finish. Later on, we put stronger constraints coming from fifth force analogies and things like that. But here, for the purpose of that talk, I found it pretty interesting, the fact that by just a few pulsars, the theory is able to put constraints on a purely mathematical proposal for giving a geometrical origin of the standard model. Yes?
Can we just move to the question session? Unless it's a very quick clarification.
In the previous thing, you had a Weil tensor square term which had a coefficient alpha and then a non-minimal coupling to the Higgs. Yeah. Maybe I can't read from here, but is the Weil tensor coefficient appearing in these formulas at all?
The alpha 0 is related to the beta. I put constraints on the betas, yeah. It's the same one. Alpha 0 is beta is the same thing.
Okay, thank you.
So there were put constraints.
Okay, thank you.
So because my friend Sumat is going to kill me if I don't stop, indeed I stop. So here are the conclusions. The implications of gravitational wave detections can hardly be overestimated. For instance, test of GR and extended gravity of theories, test of quantum gravity proposals, test of high energy physics beyond the standard model, information about nature of dark matter and constraints. I did not talk, but we put constraints on actions, primordial black holes, and all that. Information about cosmology, the cosmic expansion history, information about astrophysics, neutron star, radii, equation of state, black hole masses, and spin. And with that, sorry, thank you very much. I'm not going to.
Thank you, Myri, for a really great talk. I think we have a lot to learn about these observations and extracting information from them. So we have a few minutes for questions. It's more important than the coffee break. So I think there's one there first. Sorry, earlier, then to here.
So this was just about the final action you wrote, the spectral action.
Which final action? I put many times actions.
The last slide, the cones and the cones action. The cones action. Yeah, with the alpha 0 and
yeah.
so I mean, this alpha 0, tau 0 are just completely arbitrary.
No, they're not arbitrary. I mean, this term is a topological term, is not important. This is the term, you have the terms.
Is alpha 0?
That's a put constraint, it's a free parameter.
But then there may be tachyons or ghosts in the theory.
No, because as I said before, you do an expansion of here, the expansion of various orders here, this silly liquid coefficient. So what I take, you can, there are no ghosts because you can have extra terms that they can kill whatever comes. So it's not, you don't have a ghost here. It's not, I mean.
Is alpha 0 loop, I mean, coming from the quantum effects or alpha 0?
I don't have quantum effects here.
But then, in generic higher derivative theories, we would
they could or they could not. But if you take an expansion, you always say there could be extra terms that we have done a study here to see if there is a ghost. And if I even truncate it up to the third mod, I don't have a ghost. I can get this, I'm sorry, but this was done more than 10 years ago. I can find the reference, but I cannot remember it by heart. But we have studied that if there are negative energy states, that's what we have studied. But the details of the calculation is about 12 years ago. I don't remember them. But we can see. But it doesn't have ghost. The problems that this theory has is not really the ghost. But I don't go through that. The problem that I have is that really has is the Euclidean Lorentzian kind of mapping, which is something that people work on but has not been correctly finalized. There are other things that I can criticize about this approach, but but it's beyond the scope of what we say now.
I mean, there were other constraints like causality that Malasena and others devised that.
Excuse me?
Three-point coupling is not same as GR. There may be Shapiro time advance in this model.
I didn't get what you said.
So, I mean, if you compute Shapiro time delay, for example, in these theories, because these are higher derivatives.
Can we move it to the discussion?
I have not calculated Shapiro time delay. I mean, the Shapiro time delay but the Shapiro time delay is another very delicate thing which so far has not been done correctly. So I've not done Shapiro time delay here.
Yeah, not surprisingly, I'd be interested, of course, in the quantum, making any links with quantum gravity. So what I wanted to ask about the status of these formulas you used to analyze, possible anomalous dimensions, house of dimension, spectral dimension on dispersion relations and other things. So I'm wondering about the status of these formulas, given that we know basically nothing about, how matter and gravity interact. So I would expect, since these, these anomalous dimensions, I think they're constrained to be very close to Planckian, I guess. So why should I trust these? Where do they come from, and what why should I trust these formulas?
Which expression? For instance,
effective formulas that you presented.
The dispersion relation that I wrote down, as I said, for instance, if I have massive gravity, I know how to write this form. If I have Horava ellipses or extra dimensions, I know how to write this form. Now, I do from my side a phenomenological modification of the standard dispersion relation. If you take your preferred model and you can write it, you might cannot. But I'm saying that's what we can do. This is your job, not mine. You see what I mean? In the sense that so we model it that way, which can capture a class of modified GR theories. If you cannot write it in this form, then this, what I said, does not apply.
Right. So this is why I asked about what is this? I didn't criticize. I asked what is the status of these formulas, and from my point of view, why should I trust these heuristic formulas?
The formulas, as I said, I wrote it even as a phenomenological way.
Yes,
of
it's heuristics of capturing. They ultimately come from effective and perturbative ways of thinking about these theories.
That's. So from my side, it's not criticisms to you either, but I'm saying that that's what we cannot do. These are our tools in order to test that. If the theory cannot provide me this form, my tools do not apply. Now, if this form, if this expression, this phenomenological, heuristic expression to write it, if it's appropriate for all quantum, I don't know. It is valid for some approaches to modified gravity, which could come from a kind of quantum gravity-inspired model. Now,
it's fine. As long as you have some kind of effective.
Yeah, that's why
Description.
I put in my first slide, the title, I put quantum in lighter blue and in italics. Because
I think I missed this subtlety
Yeah,
because
because
of the
it is-
Doha effect.
because there is I mean there is still a huge gap to which
Just as a side remark, just as a continuation, I 100% agree with you that the burden is on us. In other words, people who do fundamental quantum gravity, his burden is on us to produce effects which can be tested. I mean, and as you said, what you can do is to parameterize things and put limits to the parameters. And it's, burden is on us to come up with, say, effects which are
because as I said before, I was talking with a more mathematician recently, Paula Scherer, about no commutative geometry. I said that's very interesting, and then we tried to think. We just start thinking about that, how we could write from his commutative model, how we could write such a phenomenological way of the modified dispersion relation. It might take a year to be done, it might not be done, I don't know. If it cannot be done, then this doesn't apply.
Right. Right.
Yeah.
I mean, we may not like what you do,
Yeah,
but then our burden is to sort of come up with something which can be tested. Okay. Now my question was really about the PTA thing.
Yeah.
Now the announcement that when it came in July, I mean, as you say, it was not. They were careful to say it's not discovery because of the. But still, even if we assume that it's discovery, which I believe it is, it's really what they found was that there's a background hum. And it is, I mean, my impression from when I did this reading of it is that it really would not be possible even after a year to trace it to any individual things. And in other words, there is a superposition of so many events of completely different character and so on and so forth. So I kind of feel that it's going to be very difficult to use that to really dig out any effects of the kind that you're
Right,
talking
because
about.
when it came out, and I was in I was in an environment with where representatives of Nanogram, and they were gave talks like that. And the day after came a paper. As you know, I worked for years in cosmic strings, and there is a paper around where our numerical simulation of cosmic strings is the one that fits better the EPTA data. So I was very excited because there's one paper of the collaboration which says, I mean, this fits better the data. But all that is because, so there are so many different things that can fit the data. You can have defects, you can have different masses of black holes, you have phase transitions, so it's very difficult to say what it is.
Yeah.
And as a matter of fact, that's an aside thing on what you said. We did a study with Katerina, a student of mine who has finished now, about a couple of years back, about if you have a detection tomorrow, and we are sure that this detection is not a noise, but if we have a detection.
PTA design.
No PTA, a stochastic gravitational wave background. Can I say whether it comes from superposition of CBCs, compact binaries? Can it comes from phase transitions? Can it come? We cannot. It may be able to be done with 3G detectors, but right now, with what we have, it will be impossible to find where it comes
I agree
from.
completely.
I've got a few more minutes because he's not going to be here for the discussion session. So, yeah.
Oh, okay, so if I say something wrong, don't get mad at me, please.
I give the impression that I get mad easily. I don't know.
We are waiting for coffee, so quickly to the physics.
Yes.
So you can escape easily to the coffee in case the question is.
No, it'll be on YouTube forever. So this extra dimensions test that you had, how does the leakage of radiation scale with the size of the extra dimensions? For instance,
No, this I think was, but I think, because that's not something that I've done myself, I think that this was considered not, like a constant, was not taking into account how it could change with the dimensionality where it leaks. It was just put the scale RC, which is the scale at which we are going to have this leakage to the extra dimension. But it was not, the RC was not a function of the dimensionality.
No, not the dimensionality, but the size of the extra dimensions. For instance,
the size of the extra dimension. There it was put the number of the extra dimensions. I'm talking about this the extra dimension spaces where you have small extra dimensions. Sorry, large extra dimensions. Large extra dimensions.
So I have a question regarding this PTA.
Regarding
This PTA, pulsar timing array.
the pulsar timing array.
Yes. So you were mentioning that the frequency domain of the gravitational wave is a nanohertz, but my question is that in the observation, is it important? I mean, does the frequency of the EM pulse play any role?
No. They are millisecond pulsars.
Yes.
They are the millisecond pulsars.
Yes,
So
that is the timing frequency.
that's, yeah.
But the frequency of the pulse, I'm saying, the
No,
electromagnetic wave.
what it plays important is the frequency at which your detector is going to, it operates, what gravitational waves is going to detect.
Yes.
Okay? So you have the millisecond pulsar, but of course the distance from there here is going to affect what will be the frequency. Now we work in the nanograph scale. That means that, as I said, the small frequencies, large wavelengths, and that gives to bigger orbits. And therefore, if the orbits are larger, wider, then the spiral takes much more time. If the spiral takes much more time, it gives more information to your detector.
Yes, but I was asking about the electromagnetic wave frequency.
Here I was not talking about electromagnetic
No,
frequency
the
at all.
pulsar that pulsar is
The
emitting
pulsar
the
time
EM
is,
pulse.
is the,
So
yeah,
that
it's like,
frequency.
yeah.
Okay.
Here I talked just for the gravitational waves. I do not compare, the time. I don't say anything in what I said for PTS has nothing to do with the speed of gravitons. So I did not compare the speed of gravitons to the electromagnetic spectrum.
Okay, okay.
So let's thank Mary again. Just so that I can see that. Okay, so great. Thanks for coming back. We will, so very happy to have Sudipta here from IIT Gandhinagar. And he's going to also tell us something interesting about stability of horizonless ultra-compact objects, whatever they are, and we shall learn about them.
Okay, so thanks. Thanks a lot, Shrimati and Madhavan, for inviting me in such a nice conference. And and it's interesting to give a talk after such a nice banquet. Okay, I hope I'll try my best. Okay, if the talks went back, all blame is on Sumati and Madhavan. Okay. Okay, so what I'm going to talk about is this idea that, well, we are all, I mean, more or less in agreement with the existence of black hole, but there is still possibility of some existence of ultra-compact object without a horizon. And I'll define what do I mean by ultra-compact as I move in the talk. And then the question is whether such objects are physically possible. I'm not even talking about detecting them observationally, which itself is an interesting field. But the question is whether these objects are physically possible or they are sick, in a sense that they are unstable under perturbations. Okay? So this will be the main topic of my talk, and I'll give you the answer before that most probably they are sick. It seems that whatever model of ultra-compact objects you have, they will either in linear order or non-linear order or always have some form of instability. And therefore, the time scale of the instabilities are significantly small. And therefore, probably they are not present in our physical world. Okay? Although there are caveats, which I will also discuss. So there is something called black hole paradigm, and you can summarize it in 1 second, that end state of a gravitational collapse of a sufficiently massive star. Of course, the word sufficiently, you have to clarify with the astrophysicists what do we mean by sufficiently. But theorists, we are okay with the word. Of a massive star is a black hole endowed with an event horizon. The last part is highly non-trivial, whether the event horizon exists or not, but let me take it in a simplest way, that this is all what I believe. And there are several observational support for this black hole paradigm. There are existence of supermassive compact object at the center of galaxies, and they're very consistent with the Kerr paradigm that they are Kerr black holes, rotating Kerr black holes. Then there are gravitational wave observations, as in the previous talk of the black hole binary system. The data is in extremely good agreement with the presence of black hole or the existence of the black hole binary. Then the event horizon telescope collaboration, which is, I mean, you can say that it does show that the insight is very unlikely, although it only probes the area near the photon sphere, it does not really probe the horizon, but there are indirect conclusion you can reach that inside it's very difficult to have a structure supported insight. And then there are old models and discussions of the XF spectrum for accretion model, jet models, which also supports that we are probably, what you are looking at this compact object, they are probably black holes. I mean, like there is a Kerr black hole at the center of these galaxies. So this is more or less agreed, but still, nevertheless, there are alternative of black holes which have been proposed every time in the literature. And first of all, the alternatives are to test the theory. You know, I mean, you can't test something unless you have little bit violation of the theory. That's the only thing you can constrain. And in the spirit of the previous talk, and it's very important to build alternative model so that you test your original model. Not only that, the black holes do come with some theoretical problems, and there is some community who are looking for possibility of ultra-compact object which are without any event horizon. So there are candidates exist like boson star, Procast star. They are solutions of the, yeah, please.
In your second point, you say area quantization. Like,
what
is that
area quantization? Where I didn't say anything.
In the second slide.
Second slide.
In this slide,
yeah.
in the second point. So that is with reference to like loop quantum gravity, let's say.
I'll come back to it. It will not be exactly same as loop quantum gravity.
Okay.
I'll
because that is the horizon. I mean, it's not.
Yes, exactly. So massive compact stars like boson star and Procast stars, these have been extensively studied in literature, and in fact, gravitational waves from them, whether they can, the inspiral part of the data can be supported by them. QNM part is difficult because of lack of signal to noise ratio. Then there are, of course, the solution where there is a horizon, but there is some new horizon physics and fastball area quantization. These are the things are part of the literature. People have studied what will be the consequence of this. Then, of course, there are new configurations, Grava star, regular black holes, and these are new GR configurations. For example, Grava star is kind of a system, which is inside there is a de Sitter cosmological constant, and outside there is Schwarzschild, and it turns out you can match all the matching conditions and write down an exact solution. So mathematically they are possible, and then what will be the consequence of presence of such objects? I should say not all objects like Grava star, something like that, you can't show that they come from a gravitational collapse. These are like eternal solution given to you, and then you can test it in your perturbations or something. Okay. Some of these models are actually consistent with this observation. For example, this is observations. You can show that it's only with this observation, it is very difficult to say that whether it rules out there is a horizon or not. But if you couple it with other observations, then for example, if you look at M87, if you only take a boson star model and try to fit the data with the black hole shadow data, EHT data, you can fit with certain models. But there are also jet physics. We have seen jets in the M87. So it's very difficult to satisfy both the jet physics as well as the M87 shadow data with the single boson star model. So things are very constrained. Okay? And as I said that unlike the black hole solutions of general relativity, some of these models suffer from theoretical inconsistency, and then we may be able to rule out them by stability requirement. Okay? That will be the main focus of this talk. So I should say that only with the data, it is not always possible. If you trust this model, it is not always possible to rule them out, because there will be parameters, there will be uncertainties in the data, there will be astrophysical environment issues whose modeling we don't know, which will lead to always some room to place them into a consistency region of your data. But nevertheless, there are stability arguments which are pretty strong. So what are these stability arguments? I'm going to talk about two stability arguments. So although I have chronologically called them 1 and 2, I'm first going to talk about light ring instability, then I'm going to talk about ergo region instability. Because this is what related to our recent work, and this is something which we are also trying to learn. So basically, ergo region instability is basically when you violate the ingoing boundary condition of the perturbations at the horizon in the presence of a ergo region. So if you have a rotating object, which may or may not have a horizon, but what you say is that I will not going to use ingoing boundary condition, I am going to use some mixture of ingoing and outgoing boundary condition, because it is not a horizon, it could be a hard surface, so there could be some non-zero reflectivity. The reflectivity is the amount of energy which is reflects back. For black hole, the reflectivity is exactly equal to 0. And once you do that, the presence of ergo region leads to an instability which occurs even in the linear order perturbations. Basically, what will happen if you calculate quasi-normal modes, the imaginary part of the quasi-normal modes will change its sign. This is similar to what Amitav has discussed, but remember there the boundary condition is at infinity. And here the boundary condition, the reflecting boundary condition is at the horizon. So it may be interesting that to understand the end stage of that process, to understand the end stage of this process, there may be a relationship which I'm very intrigued by Amitav's talk.
Is it perfectly reflecting or?
That's a very good question. It turns out, okay, so what Sunita asked, that is it perfectly reflecting? So it turns out, I'm going to discuss it, that if it is perfectly reflecting, like a Dirichlet boundary condition, it is always unstable, above a certain critical spin. But you can quench this instability by using what is called a partial reflecting surface. So then it's a details of modeling will come in. Then there is what is called the light ring instability. This is the instability resulted when a horizonless compact object have a light ring. So suppose the object is some, let's say a star, whatever we have created is 2.5 solar mass. So which has its own light ring outside, but it is bigger than its horizon. Of course, the dynamical stability of such objects, you can put into question. But suppose you have such object which has light ring but no horizon, it turns out there are other instabilities which kicks in, And this is called a light-ring instability, but it occurs at a non-linear level. So there is no analytical way of handling this yet. We only have numerical evidence of this instability. And therefore, for me also, it's my numeric knowledge is rather very rudimentary. So we are still trying to learn the papers there and try to reproduce this result. But it still seems to be a very strong result because the time scales of instability turns out to be very tiny. Okay, so there the idea is that if you have a light ring, inside must be a horizon. If it is not a horizon, light ring instabilities will kick in and the object will be completely destroyed. Again, the question remains, what is the end stage of this thing? I will tell you certain numerical calculation which shows some evidences of this end state, but the issue is far from clear. Okay, so let's start with light ring instability. This is GR101, and this is the effective potential of a light, what the photons is, and of course it has a maxima, and this is the maxima for Schwarzschild happened at r equal to 3m, and this is what our light ring is, the photon ring or whatever, photon sphere for spherical symmetric is. So it is an unstable circular orbit of a photon. It's a geodesic, circular means specially closed geodesic of the photon. So I copied this from Blau's lecture notes. Now it is okay. So in spherical symmetry, it's very easy to write down the equation of the light ring. Even when you switch on Kerr, things are quite complicated. That is because there is no spherical symmetry. There is only axial symmetry, and Kerr, in general, there is no closed light geodesic except on the equatorial plane, and this is a very well-known result. If you are away from the equatorial plane, there is something called a photon sphere, which is basically lights moving on various theta directions. Okay? But in equatorial plane, there exists a light ring, what is called a circularly closed null geodesic, and this can be shown as a consequence of the Z2 symmetry of the curve black hole, theta 2 minus theta symmetry of the black hole. That it has to only happen at Z, theta equal to pi by 2. Yeah. So, yeah.
Sorry, just in the Kerr case, all the other trajectories, they're also closed, they're just not
They're
circular.
closed, but they're not circular. In a sense, right. they can move on a sphere.
Yes.
And therefore, they produce what is called a photon sphere.
Yes. Shell.
Photon shell, yeah. Okay, so let's go ahead. Now, what can you define such a notion of light ring in a specially closed geodesic in a general space-time where I don't give you spherical symmetry, I give you only, let's say, stationarity. Of course, without stationarity, you will not be able to do anything. And suppose I also give you the another killing vector, which is the axial killing vector, the axis symmetry. Okay. So I write down a metric, which is most general metric in this killing vector. It's actually not a most general metric. I'll come back to it, why it is not. So GTT and GRR are functions of theta and phi only. Okay, there is no phi, sorry, theta and r only. There is no phi dependence, so I use axis symmetry. So I must emphasize that the existence of a second space-like killing vector del phi is a crucial assumption. It is required to define the notion of a light ring. As we are saying, if I don't have a phi isometry, it's very difficult to define what do I mean by specially closed orbits. Okay? And not, this metric is indeed not the most general axis symmetric, stationary axis symmetric space-time. For example, you could have written more terms with more cross terms in this metric. I have not written that. That is because what I am working with is called circular stationary axisymmetric metric in the language of world, where certain cross terms can be thrown away by the space-time special isometries by a clever choice of coordinates. But there are strong theorems, at least in general relativity, that all vacuum stationary axisymmetric solutions of Einstein's equation must be circular. So if you start with the most general stationary axisymmetric solution, you can show, because of the vacuum solution r equal to 0, you can always choose coordinate system in which the metric can be written circular way. Certain cross components can be set to 0. This is World book will have this theorem. Not only that, there is another very, very interesting paper by Nicunes, I think it's Nicunes and collaborator, I forgot the name of the collaborator. What they show that you don't only have to have Einstein's equations. If you have any theory of gravity where metric is the only field, and you can write down equations as a perturbative expansion around general relativity, then you can show, unless certain energy conditions are satisfied, if you consider, let's say, first order violation of general relativity, then the violation for circularity will be higher order. So in some sense, by adding these higher curvature terms, you can still hide the circularity into higher and higher, a violation of circularity in higher and higher order. This is a very, very important theorem. So it's basically saying any perturbative solution, corrections to curve black hole, although we don't have such solution, rotating solution, will also be circular. Yeah.
Just so this PRL by Nico and collaborators, what it shows is that any black hole solution that if you deform it back to Kerr will be circular. That doesn't mean that the theory beyond the doesn't have other solutions.
Absolutely correct. You are absolutely correct. That is what I mean. It is perturbatively connected to GR. So if you have a parameter, so you take the Kerr solution and if you deform it from there, such deformation will. But it's definitely true there could be completely other branch which does not even have a GR limit, and such branches are known at least in the spherically symmetric sector where you may not have circular violation of circularity. But that's all. That's the result it is. Yeah. Yes.
Can we, can't hear you at all. Can someone just pass this on?
Got it.
Yeah, so I may be completely wrong, but
just put it to your...
Okay. So does this thing has any connection to the violation of Birkhoff theorem also?
Okay, so Birkhoff's theorem says the spherically symmetric solution must be static.
Yes.
This is valid only for a limited class of general solutions. Okay, so this is far more powerful statement than Birkhoff's theorem. Here you are actually starting with a spherically symmetric solution. You are assuming a two killing vector, del t and del phi. Then you write down what is the most general spherically symmetric, stationary axis symmetric solution possible. It will have certain independent component of the matrix. Then if you impose an extra symmetric or circularity, it is some form of integrability condition. Okay, if you put that, you can get away certain those extra components by using suitable coordinate transformation. And for vacuum Einstein's equation to be satisfied, you can show this integrity condition. Okay, there is one very important condition which I forgot to mention, asymptotically flatness. Without the asymptotic flatness, none of this conclusion will be valid. We still don't have a generalization of this theorem beyond asymptotic flatness.
So the perturbation will not cause any effect on the killing vectors? The killing vectors will remain killing vectors?
Yeah, so this is not a perturbation in a sense of the quasi-normal mode. What you are saying is that I am changing the theory away from general relativity, but what I am saying is that therefore the solution I am starting with is a solution of general relativity, and then looking at the corrections to the solution because of the corrections to the theory. Then it turns out that the corrections to the solution can also be circular, order by order.
Order by order. Okay.
But it tells you a very powerful statement that probably the corrections to curve black hole in any modified gravity theory, if certain smooth GR limit exists, which one would expect to, would be also circular. But once you have circular, there are certain integrability condition in the geodesic equation. It simplifies a lot, and the calculations become much easier.
Okay, thank you.
Hello. Actually, I just want to get clear about this circularity condition. Two killing vectors is circularity, if I'm correct?
No. Two killing vectors tells you axis symmetric and stationarity. Circularity is more than that.
Because circularity means you can construct vectors in one plane and two of them in opposite. Like
so then it gives you these two planes are integratable to each other. So, and there's an existence of integratable two planes. I can discuss it later, but maybe it will be better because it's a long argument. Okay, it's involved. Yeah. And also, so we will assume asymptotic flatness. Now, in this, so basically, please.
Yeah, so 2 slides before you mentioned in your, point number 1, there you said like if the surface is like perfectly reflecting, then it's unstable. So is there some cutoff at which you can say that there is a
so these are all these statements are subject to certain choices of cutoff.
And that parameter is related to
That's
the reflectivity?
Yes, but depending on the model. There all the model dependence come in. Okay, thanks. So in this metric, so in that sense, this is indeed probably the most general stationary axisymmetric metric. It is safe to take this metric and work out with it, with modulo your and also it is easier. That's ergosphere. So if this metric has ergosphere, the norm of the del t killing vector goes away. So it is somewhere GTT equal to 0. This will be some surface where R will be a function of theta. Okay. Okay. Now, of course, I will assume asymptotic flatness in a very rudimentary language so that all the theorems I can apply. Okay. Good. Then how do I define closed null geodesic in this spacetime? So the definition will be this, that I consider light ring to be a null geodesic such that the tangent vector of the null geodesic is always a linear combination of del t and del phi. There is absolutely no guarantee that in arbitrary spacetime such null geodesic exists. Okay. But if it exists, it will be of this form, that it's some linear combination of del t and del phi. Del phi will make it closed, spatially closed. Okay, so it's like this kind of in space-time diagram. Okay, and then if you can actually write down the Hamilton-Jacobi, it will actually imply that this belongs to that mu is r and theta, pr and p theta, as well as derivatives goes to 0, which is in Hamiltonian-Jacobi. That is what you would expect. One can show that such light ring can be both minimum of the potential and maximum of the potential. Though for black hole case, I have shown that it is mostly, at least for Schwarzschild, it is the maximum of the potential which comes. Of course, the Schwarzschild and Kerr black holes have light rings outside the horizon / ergosphere. Such light rings are the maximum of the potential. And note that for Kerr black hole, the equatorial plane, there exists a light ring. And therefore, the question is, what about non-black holes and horizonless complex? Is it true that even if I don't know the exact structure of the solution, can I do some kinematical argument to say that there is always such a null geodesic? So then there exists a very, very remarkable theorem by Pedro Cunha and Hedero and their groups. What this theorem says is that if you have a horizonless compact object, and they define what is ultra compact, that is a horizonless compact object which has one light ring. That they call ultra compact. They are sufficiently compact to have a light ring. So this says that if you have one light ring, then there must be another. Yeah.
What if the surface of the object is outside of the second light ring?
That could possible.
And then it doesn't have a second light ring.
It has a second light ring inside. For example, this star. There is such object. So you solve the potential equation everywhere. Assuming there exists inner solutions which you know, you can show that the second light ring, there are possible models for which it can happen inside.
So even if there's a distribution inside, it has a light. Okay.
So light ring instability, I think Subrat has a question.
So can we get a mic there?
Sorry, it's related to the same question. You're not assuming that there's a vacuum solution of
No way.
So then, I mean, what does a light ring mean? Maybe light doesn't propagate inside the star.
No, the question is not a light ring. The question is whether there exists a okay. If you can put a test light inside the star, then the light would have seen that potential. That's what it means.
That gravitational potential, leaving
There's a gravitational potential of the null geodesic equation. That's all it means.
And regardless of what stress tensor you put in, this is always true, you're saying?
To prove this, no, not always true. To prove, okay, let me just tell you what is the condition of the stress tensor. You don't need any condition of the stress tensor to prove this part, that if you have one light ring, there must be another. So if there is no horizon, light rings occurs in pair. To prove that part of the theorem, they don't require any kind of energy condition. But then there is a second part of the theorem which is more important. What they show is that one of this light ring must be the minima of the potential. One of this light ring must be a minima. To prove that, they require null energy condition.
Sorry, so are you claiming that irrespective of what the object is made up of?
Yes.
Irrespective
of what?
This is the part that it's
exactly.
very hard to understand exactly how it's independent of the stress tensor.
That is because the stress tensor, if you assume this space-time, You write down Hamilton-Jacobi equation of a null geodesic in this space-time, look at the structure of the potential, and from that potential you figure it out whether the potential always has a minima and maxima. That's all.
Right, without any energy conditions.
I told you that part of the proof does not require energy condition, but part of the proof where you prove that, in fact I can tell you why. So in fact, intuitively I'll tell you why it does not. Because to prove there exists a maxima and minima, you have to only look at the first derivative of the potential, which is like a first derivative of the metric. So there is no curvature information you require. To prove whether it is maxima or minima, you require second derivative of the potential. That requires curvature information, and the equation of field equation sets in. That's the way to understand it. So here is one such model of what is called a Graf-Hofstad. This is because of some paper. So you can see that this C square is some part of the parameter of the model, okay, which, yeah.
But the field equations may be not GR.
There is absolutely no assumption on field equations here.
So when you relate the stress energy to the curvature?
Careful.
Yeah.
On this first part of the theorem, this part of the theorem uses Einstein's equation. But then people have shown that certain corrections, whenever you are using null energy condition, you have to use a field equation.
Right.
The second part of the theorem uses null energy condition and Einstein's equation, but there are generalization available now, at least for, like metric and its first derivative.
That's right. So
first derivative.
Sorry,
But the second, sorry.
I was just saying the first part, from what I understood, just relies on the metric. So you give me the metric and its first derivative maybe, and that's all.
That's
so you
all.
don't need
And
any field
no, you
condition,
need
right?
asymptotic conditions to say whether.
That's for that potential, the R goes to infinity limit of the potential.
Yes, so
But
you
then
require
you-
certain form of asymptotic condition. Otherwise, this theorems will not be valid.
Right, okay.
Yeah, but I'll give you a simpler proof. Hello.
Can we
Yes, it could be a saddle also.
Sorry,
It could be a saddle also. The saddle exists.
I mean,
You mean the saddle, right?
yeah, I mean, you're saying maxima and minima must come in pair, but it could be that with a minima you have a saddle, right? I mean,
Yes, so that turns out such possibilities exist, but it is a null energy condition which rules out that possibility.
but null energy condition is greater than or equal to zero.
So the equality condition will actually give you a saddle. You are absolutely right. That possibility exists here.
Okay. So you are assuming greater than.
Greater than.
Yeah, this effective potential here, this has nothing to do with the perturbation potential, right? This is just
No,
the
no, no.
geodesic,
This is just a null geodesic potential.
not geodesic.
In certain theories, it will also agree with the perturbation potential. Yes, certain species.
Then also the statement that it is.
No, but that is a separate potential, separate physical problem. Why should I talk about null lightning?
Yeah, that was connected with before.
Yeah.
So the second part, are you doing a self-consistent approach? Is it a solution of the Einstein equation or not?
Okay, so first of all, not me, it is somebody else's work. Yes, they are using the second part to be Einstein's solutions for Einstein's equation only,
So it's some particular stress energy tensor.
which obeys certain energy conditions. No other
But
information
is it a
is
particular
required.
stress tensor?
No.
Any stress
Any
tensor
stress
obeys
energy. Yes.
and you can get a solution to the Einstein equation?
No. See, these statements are like the statements which you prove like second law. To proving second law, you don't, like a black hole second law, zeroth law. You don't use any particular solution. You use only certain regularity conditions and some assumptions on the space-time and only the energy conditions on the matter. That's all. You do not require any specific form of the solution to prove this.
Okay, so for the first part is a particular metric which you're examining, and for the second part you're just proving that one of them is
Yes.
with a
With a-
stress tensor that obeys the energy condition.
Yes.
Okay, thanks.
There's of course one possible loophole which might be that space-time might end, the space might end before you reach the position of the second light ring. And this is what happens in some of these ultra-compact models, that there's a compact extra dimension which pinches off, so that part of the space-time just doesn't
Absolutely.
exist, so that is possible.
So in a strict sense, I'm assuming asymptotic flatness.
It might end towards R equal to 0.
Okay, here you are talking about.
Yeah, so it might end before you reach the position of the second light ring.
Absolutely. Okay. Should I go ahead?
Yeah.
Okay, thanks. Okay. So this is the effective potentials you get. So this is, given the metric components, this is the structure of the effective potentials. And the light ring equations are defined with respect to the derivative of the effective potential, where it is 0, where mu goes for r and theta. This is equivalent to us saying the first derivative of the light ring potential is 0 and gives you r equal to 3m. This is just a generalization of the same thing. It just comes from Hamilton-Jacobi. So there is an old paper, relatively old paper by Cardoso, where they have shown that whenever there exists light ring which is a local extreme, by the way, this is what the Alok was saying, it could be a local extremum as well as a saddle point. Now, the existence of local minima turns out to be problematic. If the effective potential has a local minima, Cardoso shows that certain models, what they have found that the imaginary value of the quasi-normal modes can be extremely high. They found modes by exact calculation which are very high.
Very small.
Sorry, very small. In that case, it means it's a long-lived mode. So T goes as 1 by omega I. So if it's small mode, it means the time scale of decay is very, very small. So ulta boldo, its time scale of decay is very, very large. It does not decay, sorry. So it seems mean that these are long-lived mode. And existence of long-lived mode in many, many other parts of the physics seems to indicate that this energy don't dissipate very well. And I will show you the time series data that what happens. And it was conjectured to be that there exists an instability, although this is not a proof of instability. Just because there is a long-lived mode doesn't mean anything. But it was conjectured that this will probably back react and an instability will exist. So this is the first time they conjectured that such things will be bad. Then what they do is that they actually study the time profile of the field by standing at, let's say, r equal to 40m in the presence of a minima, light ring, minima of the effective potential. So you study box phi equal to 0 equation, and also you can do it with gravitational perturbation equations. You look at the time profile, how with time, basically you study something like a Price's law in this background. And you can show that even when the T by m is quite high, particular modes don't decay fast. And this is also considered at that time the existence of a instability at the nonlinear order. Again, I must emphasize this is not a proof of instability, it is only indicative. Okay? Okay. Suppose, and later, yeah.
So, where is this instability coming from? I mean, if I take Price's decay, then at Lth mode goes as 1 by.
No, that is only for.
So it's long. I mean, it's not.
Yeah. So what happens is that now there is no maximum of the potential. There is also a minima. Yeah. Because of the minima, whenever you perturb things, you can have perturbation trapped inside this minima. In some sense, that's similar to bound state comes, and that contributes to the stability problem. But what they could able, this is now the current analysis, but at that time they could only able to see that these modes are long-lived, they don't decay. That's all.
Lowell modes are long-lived in Price's tails also, right? The Lowell modes are long-lived.
Lowell modes are long-lived, but here you can have, you can see that even high-L modes are where you can have, look at this. Here also there is a long-lived mode. So that's the problem. Yeah, I think Subrat.
This again brings me back to the previous question, which is that what if space ends before that? Then this analysis would not be valid.
So, okay. In this analysis, what they do, this is a particular model where there exists, you know, the internal rho and p. What they did is that they solved the Einstein's equation everywhere and they found an internal solution also. Now they perturb the entire space-time, including the perturbation of the rho and p, and then come up with this conclusion.
This is for a specific model.
This is for a specific model, that's what I said.
We'll move it to the questions at the end.
In general, it's impossible to come up with this.
Not going to have lunch, sorry.
I don't mind, okay.
You don't mind, but many people mind.
Okay. So this is definitely.
We have time for discussion, so please.
This is definitely
I'm not trying to stop it, but just let them be short questions so that we can.
But remember, the crucial point here that this is, if they have one light ring, there is absolutely no guarantee that why should an ultraviolet compact object will always have a light ring. Is it possible to prove it? So this is what we have proven. So we took the assumption of these calculations and we turned it out and we asked what is the condition for which outside there is always a light ring, irrespective of the theory of gravity or irrespective of the theory of energy condition. And then we proved this theorem that any stationary axisymmetric, actually circular, and asymptotically flat spacetime in 3+1 dimension with an Argo region must have at least one light ring outside. What we could be able to prove that if you have Argo region, you will always have a light ring. At least one light ring. I can't say more than, there could be more than one. At least one light ring outside the Argo region. This is the theorem which I proved with my student, Rajesh. And what it means is that any rotating compact object with Argo region must have a light ring. And this proof is independent of the theory of gravity. It does not require any theory. And not only that, there is no assumption of energy conditions or anything. Okay, so you can't bypass by saying my matter is made out of, let's say, exotic or something. So how the theorem proofs goes, so you write down the equation.
Are these also connected to gravity?
Connected to gravity means?
I mean, are these also deformations of, are these smoothly connected to GR or?
I don't need any assumptions here, but what he says is very important. But to use the circular spacetime and demand that this is the most general spacetime I can work with, I do need this assumption.
So you do need?
Not in this proof,
maybe
but
in the
in
discussion.
A second order way. Yeah.
Sorry, the proof only holds for circular spacetimes.
Absolutely, proof only holds for circular. To justify this, that the circular, all solutions of other theories are circular, I did this particular assumption. Okay, is it clear? No. So I write down the light ring equations, and the light ring equations needs to go ahead. So what I need to prove that this equation always has solution outside the Argosphere. So that's what I do. So I look at the theta equation first, and I can prove that there exists an axis, I have assumed, where G phi is 0. This you can prove for asymptotically flat, spherically symmetric spacewave because of a famous work by Carter that there will always be an axis. And you can show this H at two different values of theta must be 0. And therefore, of course, what is the theorem? It says that it is 0 in between, I forgot some preliminary theorem in calculus, okay, which says that the derivative must be 0 at some point, okay. And note that this is exactly what happens for curve. The only thing is that, so there exists a particular value of theta for which this derivative has to be 0. For curve, because of the Z2 symmetry, that plane is in the theta equal to pi by 2. But in general case, it could be anywhere, any value of theta, but there exists always a theta plane for every value of r. Similarly, I can prove that if I use asymptotic flatness, I look at the radial derivative equal to 0 equation, I need to show that this equation will always be satisfied. I can show that by using Argosphere boundary condition at the boundary and the asymptotically flat condition at the infinity, I can show this radial equation must have a 0. So what I proven is that these two equations must be satisfied at least once, there could be more than, outside the Argosphere, provided I use this boundary condition. And this tells me that a light ring equation must have a solution outside the Argosphere. So, yeah. R and L is just definition. It turns out this guy is L minus R. We can write it in this way. And you prove that this is one sign near the Argosphere, and this is other sign near the asymptotic, and therefore it must have a 0 in between. That's all. Oh, sorry. So here is this theorem. Any stationary axisymmetric asymptotic flat, let me emphasize circular, okay, spacetime in 1+3 dimension with an Argo region must have at least one light ring outside the Argo region. We have not used any field equation, any energy conditions. Proof is sufficiently general and rather simple. I wish really that if I can get rid of this asymptotically flat boundary condition. The problem with, like the first thing you try, your DS or ADS boundary condition, you cannot prove there will always be a axis, that G phi will be 0. And the Carter's calculations don't work. And it requires some sophisticated global analysis to see whether the asymptotic condition being ADS. So that proof is very important. So then, the important consequence of our proof is that if there is one light ring, the theorem by Kuna ensures that there is another, unless the central object is a black hole. In that case, none will work. And one of the light ring must be stable, and that leads to, by stable I mean the minimum of the potential, and leads to a space-time instability. And if the time scale of instability is appropriate, the central object may not exist to observe. So this is what is done by this. After we wrote this work, Kuna and Cardoso again worked out more details. And this is again model dependent. I mean, without the model, I can't do full calculation. What they did is that they took two particular models, boson star and Procas star, where objects have minima of the potential. Now what they show is that they prove they evolve fully nonlinear simulation of Einstein's equation with matter, assuming certain energy conditions. And what they prove that two models, very interesting things happen. So this is the picture. This is some numerical jiggery is there in their paper. There's a discussion why it happens. So this is how the stable light ring evolves. Okay, stable means minimum of the potential. And this is how the unstable light ring evolves. This is for the it is only for the boson star. And what they show is that after a certain time, the space-time has no light ring. Okay, certain evolution. And then, they have only one light ring after a certain time. And then they could also follow the evolution of the lapse function. I should have written this is in the lapse function. And they show that the lapse function, once it happens, it almost goes to 0, which indicate the existence of a horizon. So it seems, at least these simulations, that you start with this object, look at this light ring instability, the end result seems to be a black hole with single light ring. Okay. Again, I must emphasize this assume very, very simple spectra. For example, there is hardly any rotation in these simulations. The rotations, weakly rotating calculations there. This is also a very particular form of the potentials has been used where you can do numerical calculation, but it's indicative that if you have stable light ring, the system is unstable and ultimately it collapses into form a black hole with a single light ring. In fact, there is a theorem which ensures that for a black hole, there is always outside a single light ring. In fact, it comes from our result very trivially. You can show if there is a horizon, again by using Carter's and Hawking's argument, there will always be ergosphere outside. And I welcome you to try it. It's a good homework. Okay. If there is a horizon, there will always be a ergo region. And therefore, our theorem also comes, which says that if there is an ergo region, there must be a light ring outside. So if the horizon exists, there will always be at least one light ring. Yeah.
I don't know, is it correct? If it is slowly rotating one, that ergo region comes inside the...
Ergo region is same as the horizon then.
But it comes inside. No?
Inside? No. Ergo region is where del T goes null, right?
Yeah.
That is true for R equal to 2m, it is same.
Slowly rotating?
I mean, take the rotation to 0.
Okay.
Ergo region is always outside the horizon, provided energy conditions are true.
Okay. Yeah,
Think of card.
Because we have that UNIS one is slowly rotating one they have considered.
Who?
The UNIS paper.
No, the UNIS paper has no slow rotation
We
assumption.
just did plotting. This ergo region comes, it's like if we go with a rotational parameter larger, then ergo region and even horizon.
For card, of course, this is not true, but we can discuss later. I have to look at what you are doing. It does not fit into my intuition. Okay, so it is almost now confirmed, at least in certain models, that horizonless compact object with light ring cannot be stable. And the time scale for instability is small. So you should say, what is the time scale of instability? It turns out it is related to the light crossing time across this light ring, and it's few light crossing times you will get this instability to set in. And that's very, very important to rule out the existence of soft charge. So if we observe light ring in the sky, for example, this particular picture is consistent. It requires to fit the existence of a light ring. Then we're probably looking at a black hole inside. Okay, I use the word probably. Huh? Block, what do you mean?
Do you form the black hole from the instability in finite time?
That's what is meant. And this time is rather small compared to the mass scale of the system.
So, sorry to harp on this again. In fact, I'm very sympathetic to the perspective, but just to play devil's advocate.
Sure.
The results you had previously involved specific models. Right?
Absolutely,
But
absolutely.
the conclusion that you have on this slide is much stronger, which says it is now almost
This is
confirmed,
what
which
is
I think
called,
is not quite
this is what is called advertisement. I agree with you, absolutely. But the question is, we only have finite models, and whenever the models people have tested, this generic thing has turns out to be the case for almost every model people have tested.
I think the specific case is the fuzzball case, which, as you know, I don't like for some other reasons. But you know, the fuzzball case is one where where the space ends before the horizon forms. So that's an interesting way of getting around a lot of these no-earth theories.
This is what we are discussing
okay,
nowadays.
It would be nice to see.
It is exactly, this is something, hello. instability. There is also some result, which Amitav has shown me, that same instability kicks in. But I should also tell, although I have very little time, there is also one way to get rid of it. That is the height of this minima. Okay, so that height of this minima, you can play with it to change the time scale of the problem. So there is a free parameter. Okay, so I will also go into, I have very few minutes, I'll go quickly. So in last few years, there is this new idea of a compact object, new horizon physics, which turns out what is called the area quantization, where motivated by various models of quantum gravity. But I should again say that it's not clear to me whether, let's say, loop quantum area spectrum of the loop quantum gravity, where there is a one-to-one correspondence with this kind of thing. Okay, so this is a very generic broad, and I would probably say no. Okay, but these are very broad model, old model, which Mukhanov and Bekenstein has told. But this gives a handle to provide an alternative model to test. That's all it is. And then the system, it turns out, since the area is quantization, the transition happens only at certain finite frequency. The system behaves like a classical black hole only at discrete frequency. In other frequencies, it behaves like a perfectly reflecting object. And there are a lot of activity. Then how do I can detect it? They have suggested you should look at the inspiral and the data for the gravitational phasing of the gravitational wave signal using the tidal effects into an tidal effects thing. And then both our group, Shayak, and also Sumanto has modeled it and looked at what will be the consequence. Can I understand the properties of this quantization and all those things. There are interesting proposal to constrain this alpha, like motivated from quasi-normal mode considerations, okay, by Bekenstein and then other people also. So the question is, then it turns out there exists another instability which you cannot rule out. Once you violate ingoing boundary condition, light ring instability is the linear order, not in the non-linear order, but there exists another instability which is very important. This is something called ergo region instability, which is exactly I discussed. So basically what you do is that you put this boundary condition, ingoing as well as outgoing boundary condition here. So remember Amitav was putting here. So I am putting here, this is the light ring, existence of the light ring of the gravitational potential. And this is where the cutoff is. And then you numerically determine the imaginary the values of the quasi-normal mode frequencies. You can show that for different values of this delta, delta is where you put this cutoff. Here comes the modeling part that you have to choose some delta. You show that always, this is mod, so there is always a branch in which omega changes its sign, depending on a critical rotation. And this shows this system is unstable. Of course, nobody knows about the end stage of this instability. Okay? That is not being, because it requires full nonlinear evolution of the Einstein's equation. That has not been done. Okay? But how do, so then of course, this is first pointed out by Friedman by his old classic paper, and then Elisa Miguel and Cardoso, many people, Sumanto, and then also Enrico Baraus has also worked on it. Okay? Now what is quite interesting is that there is a paper by Elisa and Baraus. What they show is that you can play a game. Instead of a perfectly reflecting boundary condition, if you put partially absorbing boundary condition, okay, you can quench this instability. And not only that, they actually do some rough estimate by looking at the, of course, you don't know anything about the physics of this compact object, but what they did is that they took the hint from the neutron star, where the absorption is mostly because of the viscous absorption, and they created some model where you can actually show, these are all order 1 numbers for the model they were talking. You can have actually very small absorption. And their claim was, if you have smaller and smaller absorption, you can show this is the zero line, above which is unstable, niche is stable, this is stable. You can show, for this particular case, you can show this is hard, never goes to the unstable region. So they show that I can do some partial that things will be stable. So this motivates us to look at the quantum black hole. What we have shown, I'm not going to details, that you can choose these alphas to overlap various transition frequencies because of the broadening due to Hawking radiation. And you can create models for which R square is less than 1. So you can think of what will be the critical value of alpha for which you have stability. So this kind of game you can play. So, and this is the, you have to show that there, you can show, but what you can show is that there is still a frequency region of perturbation. You cannot play with it. The reflectivity will always be 1. And therefore, most probably, if the perturbation spectrum has such frequency, this system is unstable under Argoresian instability. This is still ongoing work, so I'll not commit fully to it, the statements, but I'm just flashing it because these are the results. So, a rotating area quantized black hole may not survive the stability criteria. So this is the big picture. Rotating compact object suffers from Argoresian instability in the linear order, unless we model with partial absorption. You can do certain play with the modeling. Nevertheless, a rotating compact object with Argoresian will have a light ring, which is the minimum of the potential. This is something we have proven. Existence of such a light ring will trigger light ring instability at the nonlinear order. Even non-rotating ultra-compact object will also suffer from such instability. It's very difficult to construct this model. So I will note, and I'll flash this quotation by Chandra, that black holes of nature are most perfect macroscopic objects that are in nature. The only elements of their constructions are our concept of space and time. It's a remarkable notation. It seems nature prefers such a simplicity. There are certain caveats which I must flash. These caveats are all this analysis mostly assume space-time outside the compact object, at least the modeling analysis, is a Kerr solution. This need not be true. We don't have internal solution. We don't know whether if I have a blob of matter rotating outside is a Kerr solution. At least for high rotation, definitely is not the Kerr solution. So it is important to parameterize deviation from Kerr as a function of rotation and redo all those calculations. This is something we aim to do. It may be possible that Kerr solution is modified near the surface and conclusion completely changes. This is a loophole possible. I hope it is, okay? There are people like Sumanto, Rajesh, Ajit, and Krishnendu. They are trying that, looking at the 2.5 order effect, to look at the tidal effect and try to find whether they can constrain the reflectivity or through which the model parameters, okay? But there are many, many uncertainties. All this remains what is the prior on spin you are choosing. And if you look at LIGO priors, they're like flat, okay? So the spin measurement are very imprecise for LIGO, okay, still now. So all these conclusions will depend what is the prior on other parameters you are putting, and therefore, you can play, okay. There are other possible effects at the same PN order, and then this conclusion will be, drawing conclusion will be very difficult. But nevertheless, you can go ahead and do the calculations. So this is where I end. Thank you.
Thank you, Sudipta, for a very interesting talk. So can we okay, so let's start with Amitabh and then...
Yeah, one comment and in reply to Subra's comment. So the big picture slide that you showed, the first point, the caveat is that if the object is supersymmetric, then it can be rotating, does not have ergo region, does not have ergo region instability. Okay. That possibility exists. And this is what happens for fuzzballs. Okay. So supersymmetric fuzzballs don't have ergo region instability, but they have this light ring business.
I need to look at it, but hopefully we don't have supersymmetric. Okay, no.
And the non-supersymmetric fuzzballs all have.
Okay. So is it possible to show? Can't hear. Can't hear you. What?
Yeah, but can we just...
Maybe, I think Carly has a question.
We can move to these discussions, but we can come to the
Steve
comments. Yeah, let's Steve.
Okay, so a quick comment since Abai isn't here, and then a question. The quick comment is that when you talk about area quantization, you really should be saying something like integral area quantization. In loop quantum gravity, while the area has distinct values, they are nothing at all like integer spaced.
Absolutely.
So the question goes back to the very beginning of your talk, where you were talking about various kinds of evidence for existence of horizons. You mentioned this briefly, but I wonder if you know the current status. there are these old arguments, I think by Narayan originally,
Ramesh,
that if you just look at the black hole in the center of our galaxy, you can calculate how much stuff has fallen in.
Exactly.
And if it hit a surface, you would expect the energy to come out.
Absolutely.
And it hasn't.
In the X-rays, rather.
Yeah.
In the X-rays. Yeah, that is the last point I made. There are a lot of people, Ramesh and other people have worked on it. It seems there is hardly any evidence of a hard surface. Okay. Things mostly go in. And there is something called a very interesting calculation called type 2 blast. I don't know why it is called type 2 blast, which is basically if there is a hard surface, you should see gas to go down the surface. But since their gravitational potential is huge, when they go down, they will have thermonuclear explosion. Okay. And that people have seen in neutron stars or something. That is my friends tell me. My knowledge here is only at the abstract level. Okay. But Ramesh has given talks and seminar and written papers where they claim that such kind of things have not seen certain companion object of the binary system. Okay. It seems to suggest there is hardly any hard surface. But now the improvement over it, recent improvement comes from the gravitational shadow measurement of our galaxy. What they have done is they have modeled that, okay, your shadow is at some point, there exists a hard surface just inside. Okay. And there is some source of luminosity coming out of that surface because of reflectivity. Now, what is the highest amount of luminosity and distance can support consistent with the data we measure, okay, at the very, it seems you can rule out more than what is called this Bujal limit, okay. So it seems quite interesting that you can rule out, so there is a maximum radius possible given mass, you have already measured the mass by other measures, so there is a maximum assuming certain energy condition. It seems the claim is that you can rule out that objects will be, then the object has to be smaller. If the that's very inclusive. But then there is a controversy paper by Visser, Matt Visser, who is very good at coming up with clever models. This shows that this luminosity function you have chosen, this depends on the details of accretion. You can use some model of accretion where the luminosity function is a little bit different. Then you can bypass. Okay. So, I mean, that's the status till 2-3 years ago. Rest I don't know.
Aaron?
So I'm trying to find the loopholes in the
Please.
light ring instability, and correct me when I go wrong. So the first assumption is circularity. All of this only holds
Absolutely.
for circular spacetimes. Then you can prove that you do have a second light ring.
Yes.
So then to prove that the second light ring is stable so that you have an instability, you use the null energy condition.
And Einstein's equation.
And of course Einstein equations. Yeah. Okay.
But the second proof has now been generalized into many, many collections. So there are certain other models where you look at the modified Einstein's equation.
But these are specific models.
Specific model, absolutely.
Okay. Very good. Okay, so then in some sense, if I have a null energy condition, I expect black holes anyways, right? Because
that is what the commit in that paper, exactly. That if you can, whatever the curvature corrections are, if it seems the null energy conditions, but you have to be, it's not that easy directly because there is the extra part, curvature dependent part also. This is like, I can't say if the matter of is null energy condition, the second law of black holes is true. It's still not true. You have to use field equation at some point. So I am not going to commit myself making the actual calculations are done in Einstein's equation, as corrections to Einstein's equation. If it is possible to show this is a general feature, like similar thing what Eames has done, then it will be interesting.
Okay, thanks.
And then Ellen.
The first comment I was making was just a question, actually, clarification to what Amitabh was saying, which is in the case of fuzzballs, is supersymmetry important or is it extremality? And the reason I ask is because it seems to me that what might be important for this is the long ADS2 throat, which would exist even in the extremal case and also in the supersymmetry case, but maybe Amitabh has a...
We can discuss later. There's a question.
Okay. The second question is that it seems to me that somehow ultra compact objects, these are probably very difficult to just support using any realistic equation of state for matter. So that might be just another reason why we might worry about them. And I thought That is why fuzzballs were special, because they were using a topological obstruction to horizon formation. And even though Amitabh said that some of these instabilities exist, it seemed to me that in the analysis you showed, that is precisely the case that wasn't somehow included,
Okay.
where space ends.
I have to look at it. I don't know.
Just a small comment for Aaron's question. So the null-energy condition is not sufficient to show the formation of a trapped surface.
Exactly. That's what I'm.
Yes. So you need some.
You need
PDR
global conditions.
and,
Yeah, absolutely. That is exactly what I was saying.
Okay.
Exactly. I completely agree.
Clarifying. And then my question is about the. In one of your slides, you have that the instability leads to black holes or to some non-compact objects. So I don't quite understand how that is possible, because you have a very massive object.
No, I didn't say non-compact object. In both cases, they have shown it forms a black hole.
But in one of the slides,
No. Then I
missed.
missed. Sorry.
No, it never.
No, it didn't. What they shows, they actually looked at the lapse parameter, and they found that there is a zero. It goes very close to the zero. So it indicates when there is a single light ring, at the same point, the lapse parameter is almost close to zero. Lapse or shift? Lapse, yeah. N is lapse or shift? Okay, I always, sorry, ADM, forgive me. Okay. So numerically, it seems that there is a horizon which is forming once there is a light ring. It is also consistent to the fact that most of the black holes we know there is a light ring, a single light ring outside. So that is why it's consistent.
All right. Let's thank. And we can have a. It's a great pleasure to have Aaron here with us today from Jena, and that's your current affiliation, okay? So, and he's going to tell us not everything goes in quantum gravity. Okay, looking forward to this.
Yeah, thanks, Sumati. So first on the affiliation issue, yeah, I am in Jena at the moment. It's just that I'm presenting work which is part of this DAAD Prime Fellowship, where I also spent a year in Princeton. So then I think, just like all other speakers, let me thank very much Madhavan and Sumati for organizing this brilliant meeting. I really think brilliant meeting. And I say meeting because I think what's really amazing is that there's a lot of time for discussion, and also that you've managed to bring together a group of people and create an atmosphere where we can have both actual criticism and in a friendly manner, such that we can actually learn something. I think that's when real progress happens, and so I'm very happy to now be subject to that, so in the hope of learning something. And you'll also see throughout the talk some of these pink boxes where I try to put some relations. I sat down yesterday, went through the slides again to other talks. All right, so then on the title, I picked this title here because I think what I'm going to tell you is an example in this particular model of quantum gravity called asymptotic safety, where it becomes very clear that not everything goes. If you want to be consistent with all of the observations that people have made, and I'm not talking about smoking gun effects here, I'm just talking about consistency with the physics as we know it, that's a very non-trivial constraint. And, well, you'll see this in the specific model, but I think the statement that not everything goes holds in your model as well, presumably, because otherwise it's a non-predictive thing. All right, so to start, I'm going to collapse for almost all of my talk, all of physics as we know it onto a single scale. That's a gross approximation, and I think it will break in corners of the parameter space, and I'll just make it because that's the simplest thing to do, and that's the only thing that I can do at the moment. So I have to think of all of physics in one scale, and you can give that scale an energy scale or a length scale if you turn units around, that doesn't matter. But then really the Planck scale is somewhere up here. There's actually an even higher scale, which I'll get to in a second. And then there's a bunch of scales down here. There's the electroweak scale. there's all the quark masses, there's QCD, the strong coupling scale of QCD, then there's all the all the lepton masses, the neutrino masses. Some of them might be zero, so they might be even further down. There's at some point that we reach our solar system mass scales, and then we reach galactic scales. I also want to say that, for instance, what Mary talked about today, cosmology, that's really down here. So I'll talk a lot about effective field theories. And there's very many different effective field theories. So I think it's important to make that distinction. In particular, Mary, the effective field theories that you talked about, they work somewhere down here. And often the UV completion of that theory is supposed to look like GR, such that it can evade constraints where we have very good constraints in the solar system. I will talk about an effective field theory which is the UV completion to GR, or supposed to be some UV completion to GR. So of course this could all be just one effective field theory, but then you have to go through a strong coupling regime here, which is similarly complicated than in QCD. All right, so with that perspective, the other thing that I draw from this diagram is that I will accept fine-tuning. I don't mind fine-tuning, it's all over the place here. So, and there's very many different notions of fine-tuning. To me, it's just if you have renormalized your theory and you set your initial conditions up here, then you have to put them they are not drawn in some random way from a uniform distribution, such that you get realistic physics out. This happens here all over the place. It happens, of course, between the cosmological constant and the Planck scale in the grossest possible manner, but it happens in between in softer versions in many, many ways. So I will just accept it. My way to approach new physics is trying to reduce the number of free parameters. That's, at least to me, that's more important than fine-tuning. You might disagree, that's fine. Let me also point out that for this example that is really an assumption about the UV probability distribution, we saw a beautiful example, namely the talk by Yazaman about the cosmological constant. In some sense, she had a UV theory, and the UV theory, at least on fluctuations about zero, gave a very unnatural answer, right? It gave a very non-standard answer, but once you have that theory, that's the outcome. That's the most likely outcome. So that's an example of why I think one should accept fine-tuning. Yeah, I should say, ask questions all the time. I can always jump slides in between.
Yeah, I'm slightly confused about, maybe clarify what you mean by fine-tuning. For me, these are the parameters of the theory. So when you say it's all over the place, I mean, you don't mean an infinite number of constants, or what do you mean?
Oh, I just mean that if you look at this as an effective field theory,
yeah,
and you put all your coupling values up here.
You mean just an infinite tower of terms, or what?
No. Yeah, I just mean these free parameters of the theory which generate these mass scales. They will all have very small ratios.
Yeah, I have difficulty reading the small print on there, frankly. Okay, but you're not saying you're happy to fine-tune infinitely many coupling constants?
No. I'm not saying infinitely many couplings.
Okay.
No. Just individual free parameters. I accept that they might be fine-tuned.
But you are happy if it's a lot of them?
No, I prefer a model with fewer free parameters.
But you say they are all over the place.
No, I'm saying fine-tuning is all over the place. Among the free...
Yeah, not necessarily just fundamental constants.
I'll get to the number of fundamental constants in a very specific way. Of course. All right. So then let me get back to this effective field theory that I was already talking about. This works extremely well. And what do I mean by that? I mean that we can write down the standard model of particle physics, and you'll see that in a second. And it works along a huge range of these energy scales. And just as well, you can write down general relativity, or a diffeomorphism invariant theory of the metric, as an effective field theory. And again, it works extremely well along a huge range of energy scales. Actually, the GR part, and you can couple those, that's also fine. The GR part breaks at the Planck scale. The standard model doesn't break at the Planck scale. You could just ignore gravity and go on, and then it would break at some very high scale here. This is called the U1 Landau pole. That's where things go bad in the standard model. All right, so it works, and to us, I don't need to say that, but for instance, people working in high energy physics at the LHC, they want to find new physics here. Well, that's not what this picture tells us, right? So in some sense, it works depressingly well for making predictions about new physics. But for us, that's useful, right? Because what we can do then is we can take couplings, and here I've shown you almost all, not the Lepton-Yukawa couplings, of the standard model. You can measure these couplings at observable scales. This energy scale corresponds to the electroweak scale. And you can run these couplings up. You can translate them to very high energy scales, and they probe physics up here. If you assume that there's no new physics in between, which there need not be. And so for us, I think this, what I just called depressingly well, is actually an opportunity. And we can make use of it. And I will argue that I think one should make use of it in quantum gravity models. So now you come up with your favorite quantum gravity model, and that sits somewhere up here. And really, I think if it's any proposal for a quantitative and predictive UV completion, it's now your task with your model to connect to the effective field theory up here and tell people what are the initial conditions on that effective field theory. It doesn't even need to be a clear prediction, right? Even just a distribution, a probability distribution would help. That would be interesting, that might have non-trivial constraints to all of the physics down here. And I'll tell you this story for the specific proposal of asymptotic safety. But I do think that the idea or this whole program applies more generally. All right, so let me also highlight that this is very different from direct smoking gun things. We've heard a little bit by Sumanta about possible direct smoking gun. I will not talk about this. I'll only talk about indirect constraints on this effective field theory down here.
Sir, just a small question, maybe you'll explain this, but usually when they become strongly coupled, the concept of field is... I mean, usually when theory becomes strongly coupled, there is no concept of field. It becomes ambiguous. You get something like Iving model or something.
That's right. So up here in this model that or this assumption that I'll make, I will rely on somewhat near perturbativeness, and I'll make clear in what sense I'll rely on that. And down here, there's also strong coupling scales. Things become difficult. So I agree with you. If it becomes infinitely strongly coupled, then yes.
But I mean, just to add to what Alok said, there are also strong dualities. There are also strong dualities. So if something does become very strongly coupled, we are often very lucky to find something which is dual to that strongly coupled theory, which does have an effective field description. So
maybe. I will not need that, but yeah, maybe. All right. Yes.
So does this also cover the possibility that, say, somewhere around the Planck scale or between some scales, that your smooth picture of space-time just shatters and you have some other discrete structure there? Is that also covered in this general paradigm?
In between here?
Not in between here, beyond the Planck scale.
I think so.
Or is it really UV completion, meaning like all possible scales where you send things to?
In this particular, to me, this is a particular model of quantum gravity. There I do make assumptions about, maybe it effectively describes some of the models that you're alluding to, but I don't think it necessarily does. This setup here where I'm just putting any proposal, I think that in some sense covers discrete approaches. If your discrete approach, but then you have to have a continuum limit where you somehow connect to an effective field theory.
Okay, thank you.
All right, so let me give you a very simple picture before I get into more technical versions of that, about what is it that makes this more predictive than the effective field theory itself. And that's actually an additional symmetry, and that then makes a lot of sense that it's more predictive. The model exhibits, or the conjecture is, that the field theory exhibits at very high energies additional symmetry, and that's this quantum scale symmetry. Quantum because it's only visible, it's only available at very high energies where quantum fluctuations matter. So just like reflection symmetry or any symmetry in nature, It allows you here to predict the other half of M initial's phase. Well, maybe not exactly, but approximately. Just so does scale symmetry give you additional predictive power, right? So here you can predict what the fine structure of this fern is because you are aware that it's scale symmetric. And you'll see a lot of these plots where I take the coupling, and whenever couplings get approximately constant, that's exactly meaning quantum scale symmetry or scale symmetry. And that's where the predictive power comes from. That's relating different couplings. All right. So now this is what I try to tell you about. I might have to skip things if we have a lot of questions. I'll try to give you a flavor of what this asymptotic safety is. I'll go in a historical manner. I'll then talk a little bit about the standard model matter sector. I will focus completely on the standard model, so I will make this assumption of no new physics in between. You can make other assumptions. And then in the last part, I want to talk about something very classical. I want to talk about the gravitational part of the EFT in the classical limit. And here I haven't made this connection yet, just because the EFT itself is very hard to connect to phenomenology. All right. So let's start with asymptotic safety. So I'm going to take the perspective of trying to sort this in a historical manner. And so this all starts, of course, with what's the problem? The problem before a potential proposal by Weinberg is that gravity is perturbatively non-renormalizable, right? You all know that very well. So let's look at this. You make a split of the metric into a background and a fluctuation. This constant kappa here has negative mass dimension in the path integral. So it has negative mass dimension, which is the issue. And then different loop orders will introduce you need new counter terms at every loop order, and these can come with a finite part, which is an additional free parameter of your theory. So how bad is this? How many new free parameters do we get? There's a very nice review, or I think lecture notes by Toft here. You start at 0 loop order, you generate a new divergence at 1 loop order, at least if you have matter fields present. That 1 loop order needs 2 new coefficients. You go on, you calculate 2 loop. You need this counter term, which again can come with a free parameter, and so on. So there are at each level new free couplings, and these essentially correspond to the free parameters of the effective field theory. And that's exactly the pragmatism that you can take. You just assume that at your cutoff scale, all the dimensionless couplings are roughly order 1 or smaller, and then some of them will only affect your measurements at lower energy scales to very, very tiny degrees, so you can ignore them. That's the pragmatism of EFT, and again, there's a very nice review about this. So the way that you should now think about this is in terms of what I will call an effective action. It's just like a classical action, but with an infinite tower of terms, with these running couplings in front. So these are supposed to be operators, for instance, different curvature invariants. And now you can try to project out how these coupling constants evolve in time. And I'll show you an equation with how you can do this in a second. So that's the picture of the effective field theory. And now let me already say that for a single coupling, there can be 2 different behaviors. So the coupling can grow towards larger energy scales, and that's now a measurement of particle physics at the LHC, and that's essentially the hypercharged coupling of the U1. And that's related to this enormous energy scale, 10 to the 41 GeV that I showed you in the beginning, that is beyond the Planck scale. You reach this pole here, where the coupling diverges, and then also the standard model either becomes strongly coupled or breaks down, or there needs to be something new. The opposite behavior is, of course, nicer, and that's, you probably know this plot, where you scale towards lower values, and you scale towards 0, and you can see now the first time that this will converge to exactly the 0. So it will converge to quantum scale symmetry at vanishing coupling values. And now what's Weinberg's proposal? Weinberg's proposal is nothing else but that this convergence to a quantum scale symmetric regime need not happen at vanishing coupling values. It can also happen at non-vanishing coupling values. And so now you should think of the theory space of all possible effective field theories, right? So each direction here corresponds to one of these operators, one of these invariants. So there's infinitely many of these directions. And I'll tell you about what I mean by this blue and red. Now, the proposal of Weinberg is that there is a so-called fixed point where all of the running with energy scales of these couplings, the one that I just showed you before, this one here, it goes to one of these fixed points. So it vanishes, the beta function vanishes at a particular value of couplings for all the couplings. So you'll have to search for these in whatever projection you make. For now, it's not now I haven't said anything about how to calculate these beta functions. And then the second condition is that it has to come with a finite number of so-called relevant directions. What do I mean by relevant direction? Well, you can now have two different behaviors, right? If you start from the fixed point, you can either in one direction be able to flow out of the fixed point, or you can not be able to flow out of the fixed point, meaning that you're getting pushed towards the fixed point. And this sketch here has two relevant directions, two blue directions, on which you can flow out, and therefore it's a plane surface, and one irrelevant direction. And so you want to search for a fixed point with a finite number of these blue directions and an infinite number of these red directions. And that's exactly the predictive power again. And now let me get to this point. I would classify the 80s as a search for non-perturbative methods. And here I want to highlight Renate's talk. To me, that's another non-perturbative method, because Renate is also essentially studying the quantum field theory in the very strong coupling regime. Actually, she's, in my opinion, calculating in the actually non-perturbative regime. I don't want to say again what Renate said. Instead, I'm going to tell you a little bit about why we need such a non-perturbative methods. So what you want to achieve in a single coupling is you want to achieve that this beta function vanishes. Right? We've already seen that this can happen in QED and in QCD if the coupling is zero, meaning there's a perturbative fixed point at zero coupling value. By the way, this fixed point always exists. You can always set all of your couplings to zero. That's called the Gaussian fixed point. And that's essentially responsible for the effective field theory argument. But it can only happen there. And of course, if you want to make it happen somewhere else, you need to balance different contributions. You can do that in a perturbative way, just like you asked. You can try to skim the boundary of perturbation theory and balance one loop against two loop terms. People have made this rigorous, or at least, well, maybe not mathematically rigorous, but at least they have a very strong sort of statement about three loop and four loop terms in this paper here for Gage and Yukawa theories, and they actually find such asymptotically safe fixed points. So it's not a completely crazy idea. Yeah.
Sorry, this is just a remedial question for me. Of course, in gravity, there are other constraints which in some sense are non-perturbative, which come from the fact that if you do ultra-Planckian scattering, you expect to get a big black hole. And that, is non-perturbative, and so it should be that this fixed point doesn't violate that, right? Because we do ultra-Planckian scattering all the time. You take, when a star collapses, that's ultra-Planckian. And is it clear that these kinds of asymptotic fixed points will be consistent with this experiment?
So I don't think any of what I'm going to tell you about the fixed point is rigorously clear. To the ultra-Planckian scattering, let me say, to me, this is exactly one of those questions where you shouldn't collapse everything onto a single energy scale. Because if you do a head-on collision, then yes. But if I now take a little offset and I have another parameter, like an impact parameter, the picture is not clear to me. It's not clear that the classical theory will necessarily produce an ultra-Planckian scattering.
I see. Let me just ask it this way. Is it, just standard classical black hole formation does not get affected by the presence of the asymptotic fixed point? Is that clear that it does not get affected?
Again, if you buy into the one-scale argument and you buy that an effective theory looks almost like GR, just with a few tiny corrections, then yes. Although I should say yes, up to the degree that we haven't been able, and I'll talk about this in the last part of the talk, to really do fully beyond GR numerical simulations. In some sense, you can say the last part is trying to learn that.
Just a small technical question. So when you do in QED, this, I think you already mentioned one loop versus two loop cancellation. You have this Landau pole issue that you have to worry about.
Yeah, that's just at one loop.
Only at one loop. And so here also in, okay, I guess you will.
So this is just one possibility to generate such a non-trivial zero in the beta function. Another would be to balance different types of fluctuations. And later on in the talk, you'll see where I balance matter fluctuations against gravitational fluctuations. And then the final possibility that I see, and maybe there's additional ones, you should write them down, is that the coupling that you started out with is not dimensionless. For instance, the Newton coupling. Then what you're interested in is the running of the dimensionless coupling, so it will always have a dimension-full contribution, which is an anomalous dimension. It's linear in the coupling. And then there's quantum fluctuations. And so if those balance against each other, you can also achieve a non-trivial zero. Now, that can happen at some non-trivial fixed point value. It can happen at both signs. And it can happen in a bunch of theories in principle. The whole point is that when it happens, it requires some degree of non-perturbativity because dimensions come in discrete numbers. So the term that I've shown you here, that epsilon, it will, in discrete dimensions, be order 1. So you need order 1 fluctuations. So you need some degree of non-perturbativity. All right, and therefore, I would characterize the 90s as an advance in that we have now a continuum method that has some degree of non-perturbativity. And I will call this Reuter's methodology, but I should also acknowledge that it relies on an equation which has been derived in several ways, but is now attributed to Christoph Wetterich. All right, so that's the equation. It's a non-perturbative equation. You can derive it rigorously in the field theory without having to make an approximation. So the equation is exact, but of course if you want to solve it, it's a difficult equation because in here you have an integral and here you have a differential equation, so it's an integral partial differential equation. It's terribly ugly to solve, and actually, except for specific free theories, we cannot solve it exactly. So you have to truncate it, and that's where the approximation creeps back in. Because if you truncate it, you need to make an assumption about the truncation. I will not talk much about this because I think
Gamma K2 is a kinetic term and RKs are all the higher order terms. Sorry, but then Gamma K2 is like a kinetic term and RKs are all the higher order, correct?
So this here, gamma K plus RK to the -1, you can think of it as the non-perturbative propagator of the theory. Okay. Or the approximation to the, once you truncate, to the non-perturbative propagator of the theory, and that's what we call a regulator. It's a mass-like regulator that it has to fulfill these two conditions. And those are just conditions that you need to formally set such that you ensure that your action converges as you go to infrared energies, converges to the full quantum effective action. All right.
So it has a form of one loop beta function equation, but because gamma is a quantum effective action, you're saying it's non-perturbative, is it? I mean, this equation is not one loop.
That's a very simple way of saying it, yeah.
Okay, thanks.
Yeah, so what is RK? I didn't understand what RK was.
RK is a function which you impose. It's part of your renormalization scheme or part of your regularization scheme. And it has to obey certain properties such that the flow that this generates is well behaved. But you're right about the following, that we have to show you that different choices of this regulator, right, the different shape in the middle, should not affect physical conclusions. Because here's that shape, we call it a shape function. It's in principle an arbitrary regularization procedure. All right, so now I'm going to call the 2000s and actually the 2010s as well, mounting evidence, and in the following way. So now we are truncating this infinite dimensional theory space down to a finite dimensional theory space. At least, for now we're truncating it to a finite dimensional polynomial of curvature invariance. For now, pure gravity. Now you have to make somewhat an assumption that you have a posteriori, you should justify it. And that assumption is that while we claim that the equation picks up some non-perturbative character, it's in a sufficiently near perturbative regime to make the following assumption, that power counting at high orders is still a good truncation principle, right? If I wouldn't assume that r to the power of 346 is a minor correction to my results, then, well, then I can't say anything. So this assumption, you should be careful, you should look out, and you should watch for apparent convergence in the results. And that's actually something that I would say is only now we are starting to approach that regime. All right, so I'm making that assumption. And now here is the sort of my summary of the existence of the fixed point. What we can do very well is take a single curvature scalar and go to very high order in this expansion. So up here, there's now truncations with 114. I think with computer power, this increases at some point. So you can essentially go to infinite order in one direction. What's much harder is coming up with all the different structures that you can get at one order in momentum or in one order of curvature. So at the complete level, I would say we're somewhere in between the curvature squared and the curvature cubed level. We have explored first non-trivial structures at the curvature cubed level, but we haven't explored all of them in full glory. All right, and then here I've highlighted these blue and red directions, and that's the key part. We only find a few of these blue directions, and later on, at higher order, there's only red directions. And therefore, at least that conclusion about the existence of such a fixed point seems to apparently converge. And so we can a posteriori justify that ansatz that we made. And now I'm going to show you some specific truncations. Here is there, okay.
So just to, clarify the blue and red thing. So essentially, you're saying that all of these red terms, they need not occur in...
No, they will all, so what we find is that they all have non-vanishing fixed point values because there's no symmetry that protects them. But they are these red directions that get pushed towards the blue surface. And so you make a prediction in the infrared that they are very close to zero. Or actually very close to zero is difficult because the surface might be curved, but they are very close to that blue surface.
Sorry, something I didn't understand. So in this last case where you have r to the 70 and r mu nu to the 34, how does one really compute the beta function equations? You compute some scattering process and at one loop and impose
right.
that? Or that's that other equation that you showed? But in effect, it must be the same, right, as computing some scattering process and computing a beta function?
No, it's not the, well, no, it's not the same than calculating a scattering process, for sure not.
I see. So there's some way to bypass the complicated Feynman rules that you would get with these things and still compute a beta function.
The rules are also complicated, so it's not that we completely lose complications. So we have similar, I mean, the equation, you can write it down formally, something like this. So you will have diagrams which look like Feynman diagrams. They will always have one loop only, because that's the structure of the equation. And you're going to project that onto diagrams like this. Right? And then you need to calculate these diagrams. And the increase in complexity comes with these vertices because you make, because you go to higher and higher order in a truncation.
But you only need the 3-point graviton vertex, you're saying?
No, this will also have, there will be something like this. There will be something like this as well. But you're right that at every, so the beta function for the 2-point function will only be affected by the 3- and 4-point function. And then the one for the 3-point function will be affected by the up to the 5 and so on. So it will be a tower, and you will have to consistently truncate that tower. And there where you truncate, you have to make this assumption to close the equations.
Okay, thank you.
All right, good. So just to show you some of the truncations, you can work at just the Newton coupling, and then you see exactly what I told you. There's this +2 term, which is the dimensionality in 4 dimensions. There's a fluctuating term. The only thing that matters here is that the sign comes out with a minus, because then you can balance. If the sign would come out plus, proposal is dead. Then you can go to a two-dimensional truncation, and again you find the fixed point here. You find two blue directions. You can go out of the fixed point into a plane, so there's no prediction at that point. You can accommodate some Newton coupling and some cosmological constant. And it's fine-tuned in that specific sense that if you flow out of the fixed point, you have to select the phenomenologically viable trajectory. Then you can go on, and then you start to see these red directions.
What's the anomalous dimension of the spacetime metric at the fixed point? Is it close to the engineering dimension, or it's largely different?
No, it's close to, it has roughly the size. Well,
okay.
It's not larger than 2.
I see. That's why space-time interpretation is more or less. I mean,
that's
it's
right.
Just,
but it might. I mean.
Yeah. Thanks.
Yeah. That's exactly how the naive dimensional reduction argument works in asymptotic safety.
I didn't understand this answer. I thought the previous equation would balance when G Newton became, when you were at Planck scale. That's because you're cancelling minus 2 G Newton with G Newton squared.
That's right.
So in that limit, the anomalous dimension of h mu nu, which is the one he was talking about, wouldn't that be large? It wouldn't be close to 0.
It wouldn't be close to 0, yes.
Right. So I think Alok's question was, you don't then have a good space-time interpretation because the metric now doesn't have a dimension as close to the engineering dimension. No, I think it is large. It's not close to 0.
It's certainly not close to 0. But it's also not generically larger than 2.
Yeah, not larger than 2, but yeah.
It's 2.
Some definition of it is 2. That's right. But where you're right.
Two discussions at the end of the talk as well as a whole hour of
What you're right about is that we don't have a good understanding of what the geometry looks like at this, whether it even is a geometry. For us, it's a calculational framework, and that's it. There are people who talk about, but yeah. Now, at very high orders, and I'm just going to show you this one final plot, these are all these red directions. So you see that we call the critical exponent. That gives you the sign, whether it's red or blue. And this is sort of the line where these are the 3 relevant directions that we find. And this gray line here is the scaling that you expect in the effective field theory. So here, in some sense, you see how much non-perturbativity we have in that direction. It's really just this tiny tip. And that's what makes us confident that the results, at least in that particular direction in theory space, are somewhat converged. And there's a bunch of convergence plots that I could show you, but that's it. All right, so then let me...
So the tininess depends on the truncation you started with? I mean, if you start with the r plus r to the 35, then it may not be tiny, or is that not?
Well, you say just r and then nothing else and then r to the 45? Or
no, everything up to r to the 45. You start with that.
That is part of the proposal. I mean, that's part. So you could say this. So this is the order of the truncation. So the very light blue points, they only go up to here because there's only the inclusion of up to r to the 4.
Mm.
And then, but these red points, they really include all the r to the 70.
Oh, so the truncation is 7. It's
it includes all the.
Wow.
In fact, it's a function, and you translate that partial differential equation into an ordinary differential equation. All right. So some open issues. We don't know exactly about unitarity, and that is equivalent to saying we don't know the fundamental degrees of freedom in the propagator. There's a bunch of studies recently, because this has been identified as one of the crucial open questions, and let me highlight this last work here by Yannick Fehre and collaborators, where they actually calculate the full propagator at the fixed point, and they don't find an additional pole. So they find, at least in that particular truncation, evidence that it is unitary. The other big thing is Lorentzian signature. And here I really want to come back to highlighting that we have Lorentzian models of quantization. I do think that's a very nice direction of using causal sets just to discretize these spacetimes in a Lorentzian manner. So I think there's an interesting opportunity here. And then the last one, which I've already put on the slide, is background independence. where again, I think to truly do that, we need a fully non-perturbative thing, and I think that's what Renate and her collaborators are doing. All right, so now I've spent already 40 minutes with your questions, and let me now jump to phenomenology. So I'll be very brief on the standard model side.
Thanks for being so good. Now you remind me.
So I'll try to talk about the following, that if you're performing the effective field theory around the free fixed point, that's the one where all the couplings are 0, that determines a certain scaling below the Planck scale. And according to that scaling, you will just get some parameters which are observable and some which are not observable. And so the ones which we're interested in are, of course, the ones that are observable. And then your model, or in this case, asymptotic safety, will give you some predictions about some of the parameters. So for us, there will be 3 free parameters in the gravitational sector, potentially some in the matter sector, and the others will be predictions. And only the overlap here will be potentially observable predictions, and those will be the ones that I'll focus on. Just by analyzing this effective field theory, essentially just by power counting and looking at the marginal couplings, these are the standard model couplings, then these are what I will call the quadratic gravity couplings, and a potential non-minimally coupling of all scalars to the Ricci scalar. These, I think, are the potentially observable, interesting couplings in that setup. All right, and now let's quickly move through the matter sector. I will completely skip that just to say that the whole question of existence of the fixed point is affected by matter degrees of freedom. So again, not everything goes in this approach. I will just focus on the viable infrared phenomenology now. So now I'll come back to these beta functions that I've showed you in the beginning. So what we now want to achieve is we want to make them all somehow get 0, get constant at very high energies. So these are the one-loop beta functions schematically of all the standard model couplings, gauge bosons, Yukawa couplings, and the Higgs quartic coupling. And well, now you expect that above the Planck scale, you have some contribution to gravity. And if I remain in a regime in which the standard model couplings remain perturbatively small, then the leading corrections will be those which are linear in the standard model couplings, because the next to leading order will already be coupling squared, where this coupling is a small coupling. So that's why I expect that the leading order corrections are these parameterized by this Fg, Fy, and F lambda. And there has been a big effort to calculate these contributions from this non-perturbative framework, or somewhat non-perturbative framework. What we find is that in many, many different truncations, we're very confident there's even structural arguments for why this F lambda is supposed to be negative. We're kind of sure that this is supposed to be positive or equal to 0. The or equal comes from gauge dependence. And then it gets even more murky for the Yukawa couplings, where really we only know that it's going to be positive if there's a mechanism which makes gravity weak in the interaction to the matter sector, which is somehow an assumption that I've baked into this claim that this is the leading correction anyways. So we have some evidence for such a mechanism, and I will not get into that. But if that mechanism is fulfilled, then it seems also that this contribution is positive or 0. All right. And then let's dive into phenomenology. So in the Higgs sector, this is started actually before the Higgs was measured. That's something that Christoph always pays attention to saying. You can connect now the running at high energies, right? So this one here, it will have a fixed point at lambda equals 0, and at that fixed point, this F lambda smaller 0 will make this fixed point one of the red directions. So I should have made this flow red. So it gets pushed to the fixed point values as you go to lower energies. So you see a lot of initial data is predicted to be very close to 0. That's the predictive power. So if you would push the cutoff scale to infinity, you would find exactly 0. And that then needs to be connected to the running below the Planck scale, so below 10 to the 19. Notice that there might be threshold effects now. So we're not exactly sure how it connects. And then it gives you some prediction in the infrared. And that prediction is very close to the observed value. Actually, I would say currently it's a little bit in tension. It flips a bit with the current experimental data.
Just quick question. F lambda depends on G Newton and also other couplings, all the other couplings, matter couplings, or?
That's right.
Yeah, okay.
All right, then let me get very quickly to the gauge Yukawa sector. So you can play the same game for the gauge couplings, and you'll see again that there's some predictive power because there's an infrared attractive fixed point, one of the red directions. You can play the same game for the Yukawa couplings, and again, you'll find that there are attractive fixed points. You see that trajectories get pushed towards these fixed points. Now, there's an additional effect that these two, the top Yukawa and the bottom Yukawa, or actually any generation of Yukawas, will be split because this one is now non-vanishing. And so, actually, this now gives you predictive power even if you don't know the Fs, even if you haven't calculated the Fs, because now you have two different Fs, Fg and Fy, but you have three predictions. So there's a non-trivial statement here, even if I don't know the Fs. So now I go to the infrared and I measure what the Fs would need to be in two couplings, and I'll show you the third. So these are now the two Fs, Fg and Fy. So I put in Fg. Fg is just a band, an observational band, because it doesn't depend to leading order on these other couplings. But the Yukawa coupling, the top Yukawa coupling, is somewhat a bent band. And now what's non-trivial is that the third coupling has a crossover overlap. Sure.
There's something that's confusing me, so I'd really appreciate if you could explain this a little bit. In the case of the gravitational constant, there was a beta function of 2, which you somehow managed to cancel by adding higher derivative terms. Now here you're saying there's this linear contribution that's coming from standard model couplings, but here if you change something slightly, the asymptotic fixed point will go away. And that's somehow something which is confusing me, because couldn't one say, well, you add more terms or something and you'll still get some fixed point, maybe the different truncation, even if, or maybe I'm just not understanding something in what you're saying.
What you're getting at is exactly this assumption about that there is a weak gravity mechanism, in a sense that these Fs that I've shown you, that they're all small compared to the size of the gravitational coupling. And the way that works is that we think that all the higher order terms introduce an effective mass in the gravitational propagator. And that makes the gravitational interaction with the matter sector very weak.
I see. So somehow the gravitational terms can cancel the big 2 for the gravitational coupling, but they can't cancel these Fs. That's somehow. Okay, thank you.
Yeah. All right. So let me not dwell on the standard model more, because I think we're starting to run out of time. And I do want to tell you a little bit about the gravitational side. So I think that the standard model is pretty promising. It actually doesn't work out exactly in a sense that we predict all of the standard model couplings, which at some point I think was the hope. It features intriguing structure with explanatory power. It doesn't work exactly. It looks UV complete, but not with exact predictive power. And there's by now I think there's even some one-loop tension with the most predictive fixed point. All right, so let me very briefly get to the gravitational sector. And here I'm really going to talk just classical dynamics, because I'm not convinced that we understand the effective theory at low energies well enough to make a connection to the UV. Let me also highlight that we saw the talk by Mary where she was talking about parameterized tests. I think this really is a way to sort of obtaining reasonable full waveforms in the effective field theory of gravity. So what do I mean by the effective field theory? That's the first question. Well, of course, I'm going to write down a tower of curvature operators, but what are the propagating degrees of freedom? The standard assumption is there's 2 propagating degrees of freedom, just the graviton. If I go on, formally, I now find more. Actually, if I just expand in curvature, I find 2 plus 1 plus 5, and I do find a ghost. We had the ghost already a little bit. Actually, this doesn't increase anymore. If you add more and more curvature invariance, you remain even up to infinite order, you remain with 2 plus 1 plus 5 degrees of freedom. Only if you add covariant derivatives do you get more degrees of freedom. So now the first in some sense, you can also interpret the results as the question, is it viable to take these degrees of freedom seriously? And of course, then the first question that people ask is, what about the Ostrogradsky theorem? Because now this degree of freedom here has the opposite sign kinetic term from the usual metric. And I'm going to tell you a short thing about why I think that the conclusion that this is completely ruled out is a little pre-made. And that's because usually what people say is, well, there's an opposite sign kinetic term, there's an Ostrogradsky instability, all such theories must be unstable. Well, that certainly is not true. If I try to come up with a more refined version, all non-degenerate, right, I can include constraints, higher derivative, and this is also just a statement about classical point particle theories, exhibit runaway solutions. That's another form of the statement that I've heard. So now we're already not anymore in field theory, for sure not in quantized field theory, we're just point particles with opposite sign kinetic terms. And that statement is also not true. I'm not debating Ostrogradsky's theorem. Ostrogradsky's theorem, to my understanding, just tells you that the Hamiltonian of these higher derivative classical point particle systems must be unbounded from above and below. Leading to a runaway is physical extrapolation of the theorem, and there are now counterexamples to that statement. So there's a nice paper from 22 by Cédric Defayet and collaborators where they show that in this point particle system you can have a globally stable, meaning you pick some initial conditions, any initial conditions will remain in a finite phase space volume. And we've extended that now to a much larger class of models. There's a particular Hamiltonian. These are integrable, which lets us actually prove that statement. There are certain, they have to have a certain type of form. And then there's conditions on these free functions such that we can prove this global stability. It contains polynomial subclasses. So here's the first two non-trivial orders. That doesn't look terribly complicated. But of course, there's certain relations among x and y which have to be obeyed. We now understand some of the physical conditions, and that's what the phase space pictures look like. That's just an example. Yeah?
Can we just finish with the talk and first question to Alok, second question?
Okay, I'll be quick with the rest. Let me just say that this means that there are counterexamples. I also think that integrability is not the necessary condition. That's what numerical results suggest. Field theory extensions we're working on. Quantization is a completely different issue. I have no strong statements about quantization. So now I'm going to take this theory, and you can interpret it in very many different ways. You can interpret it as the marginally relevant directions of this asymptotically safe scenario. You can interpret it as the fundamental theory really of that theory. You can interpret it as the leading EFT corrections of a theory with these ghost modes, of a theory without these ghost modes. These are all possible interpretations. All I will do is I will take this classical theory and simulate it. I'll skip the linear dynamics. We understand the branches of solutions in spherical symmetry. I'll completely jump that, because I do want to say a few words about the nonlinear regime. So we now understand the nonlinear dynamics, or at least we can simulate the nonlinear dynamics in that theory, by which I really mean that we have a well-posed initial value problem for the theory, formally for all orders of the couplings, a locally well-posed initial value problem. And the reason that we have that is thanks to Noakes. Let me very briefly tell you what well-posedness is. We mean that we can put initial data on a time slice in a 3+1 split such that the evolution exists for all future time. It's unique and it continuously depends on changes in the initial data. For general relativity, we discussed the book yesterday. It's an amazing book by Yvonne Choquet-Rohan. Actually, I will use part of that book or Noakes uses part of that book in the proof for the quadratic theory. But really, at that point, that theory is at the exact same level as general relativity. And now the difficulty is finding the right gauge to make it work. But it will be just the same gauge as in GR. So these are the equations of the theory. I've already reduced them to second order. Actually, I think the fourth order equations are quite interestingly related to the Bach tensor. So the Bach tensor also appears in this theory. That actually helps you to classify potential solutions. This is the second order version, and I will now reduce the order further to make it a well-posed system. But what you can already see is that not all equations contribute to the principal part of the other equations, and that's exactly what makes it well-posed. So you can define first-order variables, and then actually you can take another derivative and you can make that system quasi-linear diagonal. And then it fits into a generic proof, and there's actually a very nice, I would really recommend the second book of Choquet-Brouillard and DeWitt-Moret, where they have a generic sort of statement about what type of integer structures on the principal part need to be present such that this theorem holds. And it holds in that case. And therefore, at least in this formal sense, it's a well-posed thing. And so now we take that, I'm going to skip the details. The equations look ugly, but we can put them, we can implement them on a computer, and we can simulate black holes in this theory. And I should give credit here to Hyun, who actually knows much more about these simulations than I do. I'm only just learning how to deal with them. The interesting bit is now what happens, so first, all of this is numerically stable, which means that it looks like we have a well-posed initial value problem. Not get into the details. What is what we understand? We only for now have simulated vacuum solutions. And the vacuum solutions are the same vacuum solutions. We've only simulated vacuum solutions of GR as initial data. So we've taken Kerr black holes, we've made a binary merger and stuff like that. So what we understand is we recover the linear instability, which I've skipped, meaning that there's a linear instability which has exactly the same form as the Gregory-Laflamme instability for higher dimensional black holes. It leads to an unstable regime in parameter space, and if we go to that unstable regime, we recover that instability in the numerical simulations. So here, the red one sort of tuned to the peak of that instability timescale, and on both sides of the instability, we can't see the instability anymore. On one side because it's very, very slow, and on the other side because it actually looks stable. So what this also tells you is that there seems to be no other growth mode present, because now really it's a 3+1 simulation. All potential modes are excited. And indeed, we can even simulate full binary mergers in that theory, and it seems that there's a stable GR subsector of the theory if you go beyond this bound of the linear instability. So this suggests that this quadratic gravity theory can mimic vacuum GR. That doesn't tell you anything about the non-vacuum GR, and I do think if we want to constrain these couplings to learn something about the UV, the non-vacuum solutions will be critical. And that's exactly what we're trying to do next. We want to go and we want to include matter and look at gravitational collapse. Actually, there's a different framework of simulations where they're also trying that initial data, and I was at a conference 2 weeks ago to sort of work towards comparing this to dissipation frameworks where the equations are just brute force made well posed, and trying to understand field definitions so that eventually we can hopefully make Mary happy and produce some actual waveforms in these theories. And I think with that, I'll leave the nutshell slide. And sorry for going over time.
Thanks for a really interesting talk. We have time for lots of questions, so 10 minutes before lunch. So let's start with Alok, who is the first, and then Suvrat, and then we'll go on to other questions.
Hi, thanks for a very nice talk. So about the last section, maybe I just misunderstood. So if you do usual one loop correction to Einstein-Hilbert action, just the standard, we will obviously generate higher curvature terms, and they will all be Planck scale suppressed.
Well, that depends on the initial conditions.
Right. I mean, if I just do the one loop, usual one loop perturbative computation, right, then all the
if
irrelevant
you then pick order 1 coefficients at the Planck scale, then they will be very suppressed.
They're very exactly. Thanks. Yeah. So then, so your quadratic gravity, I thought, because effectively, I mean, all the coefficients of these higher curvature terms should be exactly like that, right? That they are in the low energy limit, their Planck scale suppressed. So why they should affect the classical?
Well, so there's now many different ways in which you can read that, right? If you want to talk about an EFT of just the gravitation, just the spin to massless graviton, then I think the answer is yes, they should be small enough such that the physical extra degrees of, the unphysical in that scenario, extra degrees of freedom that you have don't affect.
Yeah,
and then actually this instability, this linear instability is outside of the regime of validity of that EFT.
Yes.
But what I'm saying is maybe you can take the other degrees of freedom serious as well.
Okay, thank you.
So, this is a slightly related question. So let me just explain what I understood in the perspective of the last part, and then you can correct me if this is not correct. What I understood is, in the usual EFT framework, we would say there are always only 2 degrees of freedom. And all these higher degrees, higher derivative terms, we would treat as perturbation. So for instance, in electrodynamics, we have a radiation reaction term that gives us a runaway. But the way we would deal with it is we would say, well, first compute the classical solution, ignoring that, and then compute corrections to it by looking at the expectation value of that term in the classical solution you computed. And if you do that, then of course you don't get a runaway. So that would be the way of treating it perturbatively without trying to formulate the initial value problem a priori, including that third derivative term. But what I understood here...
I'm not sure about the last. Why would you?
Well, in effective field theory, in electrodynamics, if you took the A dot term, the way you would deal with the runaway in effective field theory is you would solve the equation without ignoring the A dot term, and then compute just perturbative corrections to it by evaluating the A dot term on the background of that you had already solved. And if you did that, you would not get
you're only treating the perturbative regime.
Exactly. So if I understood correctly, the reason you wanted to do all of this is because you want to do something in a non-perturbative way.
Yeah, but not because I want to, but because these systems, they enter they clearly enter the non-linear regime of gravity.
Right, I understood that. So then maybe something I didn't understand. Okay, thank you. So that was what I had understood also. That's why you wanted to do it non-perturbatively. What I didn't understand was your counting of degrees of freedom. You had all these terms that went up to r to the 70 or whatever. And then why don't you have to specify the value of the metric, its time derivative, and all the way up to 70 time derivatives?
That's a very good question, and I was also surprised by that, which maybe I shouldn't have been. The increasing order in curvature doesn't increase the order of the differential equation. The differential equations will always be fourth order differential equations, irrespective of how many of the curvature invariants you add. Because you have each of the curvature invariant only comes with second order, and then you take 2 functional derivatives, so you can get two free covariant derivatives, which you can. So what would give you more degrees of freedom is adding more covariant derivatives in. Exactly. Oh, they will appear. The question is now again this. I think it's again related to the question of whether there's different directions that I should not collapse onto each other, because one to me is curvature and one is momentum. If these two align, then I should just count all the momentum or curvature powers equally. If not, then maybe it's an interesting idea to go very high in curvature, but not very high in momentum. I think one way to see it is, and that's actually how people in quantum field theory at colliders do these things, when things become slightly non-perturbative in the QCD regime, you write down the invariance, so that would be the curvature invariance for us, and then you put form factors, free functions of the momentum in front, and you try to determine the shape of these form factors. And that will give you how many poles are in that respective property.
What's special about momentum? That's special in the usual Hamiltonian formulation because you have a second order differential equation. I mean, momentum is special in the usual formulation because it's the first derivative in a second order differential equation. But now you could also add terms which look like d mu r, which is the derivative of the momentum, and square them, and
That's
those
right.
would also be allowed. So, this, I mean, it's not even clear that momentum itself is special anymore.
That's perfectly right. In general, it's not. Well, so let me say one more thing. At the quadratic level, the truncation is still complete. You can absorb something like box R into the terms that I've written.
Yeah, so first I have two questions, and one question is related to the black hole solutions in this theory, the quadratic gravity. If I remember, there are some exact solution exist when linear order in the coupling. People have solved the equations and got the solution. Do you know if there are any rotating solutions or something like that
so
exists?
I think I'm aware about the solutions in the literature. I think the status is that, of course, all GR solutions are solutions. Then there's a non-GR branch of solutions, which is not an exact solution. It's known numerically, and it's known, you can approximate the numerics with some approximate analytical functions. And there are certain classes with the Bach tensor, I don't know, Yajay left, but with the Bach tensor you could, they're over there. You can classify certain classes of solutions, but they're not black holes.
Okay.
And they are also known exactly. There's a Bach vacuum and stuff like
and
that.
Is it possible
And that's all spherical symmetry.
Okay. And does it possible to show there is a consistent internal solutions like stars or something like that in this theory?
There's not much work to my understanding on that. Okay. And the reason I think is because people don't take the ghost degree of freedom seriously. Because all of these solutions, they will break the just graviton EFT. So if you don't buy into the maybe ghosts are not that bad, then I think it's correct to say that these are maybe not that interesting.
Thank you. Thank
you. Yeah, you're trying to understand the setup. So in one of the slides, you had Gregory-Laflamme instability.
Yeah.
Is that in 5 dimensions or what is that?
That's very good that you ask. So by that I just mean that the linear perturbation equation looks really exactly, it's the same equation as Gregory-Laflamme. What that tells you is that you have a background which is the same, namely just a Schwarzschild black hole, and you have one massive mode on that background. In the usual Gregory-Laflamme picture, that comes from compactifying the 5D thing down to 4 dimensions. Here it's a 4-dimensional setup, it's just a higher derivative theory. Okay. To me, this just shows you that the linear dynamics of very different physical situations can look the same.
One more question related to what Subrat was asking. So in your equations, you do have 3 time derivatives. Like you have to specify 3 time derivatives to evolve.
4.
4. So the initial data consists of
more than GR.
More than GR.
Yes. That's why we have additional degrees of freedom.
So I have 2 questions. The first one is that you showed some very pretty diagrams which look like, reminding me of the Hofstadter butterfly.
I showed lots of pretty diagrams.
No, but those 2 were really nice. Which looked like the Hofstadter butterfly, but I didn't really understand what was going on there.
So which ones are you referring to?
You know, the real pretty ones.
I can go back and you say.
Yeah, keep going, I'll tell you. Yeah, I mean, near the end. Phase space,
the black hole phase space.
Yes.
I skipped over those, yeah. This one.
No. Phase space diagram.
So is it something that we can wait for discussion session or?
I mean, I can wait. Okay, I'll ask a second question then, which is that in the context of, let's say, ADS-CFT, right, which some people think is a useful approach. If you were to apply these considerations to the gravity theory in the bulk, right, it would have some implications for the boundary theory also, right?
That's the proposal, I understand.
And so, I mean, have you thought about that? Has anybody looked at that?
So I have not thought much about it. This was actually a confusion we discussed yesterday, because to me you can construct classical theories which do all sorts of things. They break the initial value problem, they do different dynamics, and I don't see how you can always find that on the boundary. But I don't know much about this, I'm just confused about some statements.
No other questions? Oh, is there one? So that we can, this is time for discussion.
I just had maybe a technical question. The RK that you introduced in the beginning was the regulator, as you explained.
Yeah, it has nothing to do with curvature.
Yeah, I know. But so that's some smooth cutoff, as you explained.
That's right.
But then I guess when you do BRST analysis, and how do we ensure it's gauge invariant? Your effective action is finally gauge invariant.
That's a very good thing. I could have put that as a 4th point. The regulator breaks gauge invariance, so we have to ensure that this regulator breaks it.
Sorry, so, yeah, there are also other proposals. So in my paper with Eduardo D'Angelo, actually, we propose something which doesn't break the gauge invariance, but it has other features. So
Just wanted to make sure that the extra degrees of freedom you get don't come because you broke gauge invariance somehow in your
Well, so in
analysis.
some sense, the last part with the
Yeah,
extra
it's
degrees of
independent
freedom is
anyway.
completely, I'm just being agnostic about the degrees of freedom.
I think just to comment on Deepak's question, I think that this is not quite how ADS-CFT would work, and that's because string theory has a different way of, I mean, the assumption you made here was there was no new physics, right? So within the degrees of freedom that you had, you wanted to get a fixed point that was some non-trivial fixed point. But of course, in string theory, the mechanism for softening the gravitational scattering at high energies is you introduce a lot of additional degrees of freedom, which are these strings, and that's what gives you the softening at high energies. So that's a very different proposal, and that's what ADS-CFT suggests would happen. That, I mean, in these models that you would get all of these additional degrees of freedom, and that's how you'd get some very soft behavior. And so this is a different approach, all I'm saying.
Well, maybe we can take this to the discussion, but I do have questions back,
Okay,
because
sure,
it seems to me that the ADS-CFT proposal makes no reference to string theory. It's just the statement that bulk and boundary are equivalent.
Okay, it's true, but we can discuss more. I mean, there's specific things. Yeah, you're right. So maybe you can accommodate this in some enhanced way by looking at some exotic kinds of CFTs. You're right. Yeah.
We'll reconvene at 2. Oh, this beautiful picture. Okay.
Oh, this one.
Okay.
Ah.
So can we just, please talk about it and bring it up in discussion. Just do return your badges. Everybody knows who you are by now. Or they should, but you can just return the badge.
Stable path integral, and where the fluctuations, which I have not covered in the paper, but that is the main aim later on, where the fluctuations are well behaved. So I'll start with some introduction, followed by a review on Picard-Lifshitz, and then the mini superspace approximation, which I will tell what is it, basically reducing the metric into something 2 degrees of freedom, and just writing a path integral, computing the path integral, followed by a saddle analysis, which depends on Picard-Lifshitz review, and then a summary. So there has been a resurgence of interest in quantum cosmology lately because of the new tools of Picard-Lifshitz that have come up, and people have started using those methods of complex analysis and in analyzing the path integrals. So what we do, we take a fresh look at the problem and just address it with various boundary conditions to see what is it the path integral tell us. So as a starting point, we just play around with the path integral of gravity for the cosmological space-time. So this has been studied before in Euclidean framework, and what we do is basically we directly target the problem in a Lorentzian signature. The issue is of the convergence, which we will discuss, and how to find the convergence of this kind of a highly oscillatory path integral. So in standard flat space-time QFT, the idea is that if you have no gravity over there, you just have matter fields on the flat background. Basically, you do a Wick rotation of the time coordinate, and you go to a Euclidean QFT, and where there everything is well defined and can work out, and then come back again to the Lorentzian. So you have starting this thing, you have a path integral over some matter field. You go to a Euclidean by doing a Wick rotation, and the Feynman I epsilon prescription, which you might have heard before also in QFT, helps you in doing this thing sensibly and carefully, and that's the Wick rotation procedure that is we learn in the textbooks and in the course of QFT. But these benefits, they exist only in flat space-time and do not get inherited for the generic curved space-time, and where the gravity is also involved, and the space-time might be dynamical. So, but there are certain techniques called Picard-Lifshitz, which is basically just complex analysis of functional integral. Yes?
About your previous comment, suppose I have a static time-dependent space-time and look at the quantum fields and that space-time. I can do path integral, right? There is no problem.
Well, in some approximation, certain aspects you can do, but you cannot do the full exact thing. You have to resort to like approximation and those things.
The convergence issue is same as that of the flat spacetime, right?
Kind of, yeah. But your worry, if you are looking at just the UV part of the, so that thing probably we can, because anyway in the ultra short distance we will be going Euclidean anyway. So there basically we can tackle anyway. So, but yeah, I mean, we are just going a little bit beyond that, trying to do the full path integral, not just under certain approximations.
I think I've seen some theorems, like if it is a globally hyperbolic spacetime, things can, at least the matter part of the path integral may be well defined. I don't know.
Okay, we'll talk about this.
Yeah, globally hyperbolic is no, well, it's not a restriction from a classical point of view. So I don't think there is any well-defined Wick rotation. The matter part, but anyway, he's interested in the gravity part, right?
So Subrat has a question.
I missed something in the discussion that followed this. In the gravity part and flat spacetime, you still, I mean, I thought this whole problem arises because there's a conformal mode which has the wrong sign kinetic term.
Right.
So that occurs in flat space or de Sitter space anyway, right? So this problem is also there in flat space, I suppose.
Yeah. So, okay. So some techniques are there, which is basically complex analysis for functional integrals. And that allows you to get some handle over this kind of oscillatory integrals. We will learn it in shortly what that thing is, but yeah. So once we have a control over such a kind of a function integral, then we can ask certain more questions, like what are the boundary conditions which will lead to a stable universe. So back in the day, quite some time back, Hartley and Hawken, they addressed the same issues in a Euclidean gravitational path integral, and they addressed this issue of boundary condition also. They proposed something called no boundary universe, where the universe starts from nothing. The size of the universe is 0 at initial, and then basically the path integral is done over regular geometries which are non-singular. We will come back later again on this topic. So you have the standard Euclidean gravitational path integral like this, where G is the metric of the action. So so the action is like a functional of G mu nu, and there is a boundary condition I have given. Now the relation, I mean, in principle, one can just compute this thing, but then the issue is like whatever we are computing, can we just like go back in the Lorentzian, and whether whatever you are computing in the Lorentzian directly, whether that thing and what has been Wick rotated, are they related with each other or not? So that thing is not very well established. And this also suffers from conformal factor problem.
So comment, so I mean, work I was involved in 2D, you can explicitly show that the two non-perturbatively solving the path integral in either signature gives results in different universality classes. So in 2D, we know more.
Okay. So in 2D, like so if you do a rotation over this thing, a Euclidean one, and go to the Lorentzian, or you compute the directly Lorentzian one, the two things will not be same.
Well, the thing is, of course, as you pointed out, there is no general Wick rotation. So, so people were always struggling, even, what should we be comparing? in 2 dimensions, right? For instance, in CDT, you can define continuum theories coming from a lattice theory. In Euclidean signature, you get Liouville gravity, but you can also do it in Lorentzian signature. In that Lorentzian signature, there exists the Wick rotation. And then you get a Wick rotated, of course, then Euclidean path integral, which you can then, whose conversions you can discuss with standard methods. And those 2 things then turn out to be inequivalent.
I see.
So the Wick rotated Lorentzian is different from where you start out in the Euclidean regime.
I see.
So there is an explicit example in 2D. So I think that's quite beautiful, actually. Yeah. No, not at all. Yes, it is briefly speaking, because the configuration spaces of the Wick rotated Lorentzian things is very different from starting just in the purely Euclidean objects. No, it's just different in terms of its cardinality even. So not just factors of I thrown in.
So yeah, my question is actually, if you have a path integral and the variable I would imagine is the number count is the same, right? So I would expect that if you're integrating along the imaginary direction as opposed to this thing, and if your answers are different, there should be some kind of a pole or something sitting in between.
Well, that's the intuition from QFT on a flat background, so that doesn't really apply here. So there is. It's a longer discussion here.
Yeah, there is a discussion session after the talk, so we can have this.
Yeah, you have to stay for the discussion session. So so the thing is, so these issues, they motivate to study the gravitational thing directly in the Lorentzian signature and not the Wick rotated Euclidean. There is no conformal factor problem over there. And because whatever conformal factor problem you will be seeing there is basically comes with a I in front, which will be oscillatory. So the only disadvantage would be because this thing is a highly oscillatory function and its convergence is not very clear at the moment. So we have this particular phase e to the power is, and it is definitely not absolutely convergent, but consider following example. Now this series is definitely not absolutely convergent, but it's a conditionally convergent series, which is convergence to log 2. Can we have something similar for this also? So that is basically answered by this particular basically complex methods, which are generalizing things. So it tells you there are particular well-defined contours along which, if you look at the behavior of this particular function, e to the power is, it basically decays like a Gaussian. And as a result, one can do that integral along those paths. We will see this in more detail as we proceed with the further things. Let's do the review of the Picard-Lipschitz. So let's start with some small examples. So we have this kind of a complex integral. Now S of z is just a z squared thing. So what I do is basically ask the question, what are the critical points of this function? Which is in the h bar going to 0 limit, basically s prime 0 will tell you z equal to 0 is the critical point. We write z as x plus iy and look at the real part of this function. So this is minus 2xy. Now this line y equal to plus x is the steepest descent line. So because this function, if you look at just the real part of this thing, it comes with like e to the power minus 2x squared. So along this line, this particular function behaves like exponentially decaying one, and along the line y equal to minus x, it behaves like this thing. So this basically tells us that maybe if we do this particular complex integral along these particular lines, perhaps we will be able to get a sensible answer. And these lines, basically, they have a name. These are called Lipschitz timbals. Let's do it a bit more generically. So we have a generic complex integral where s of z could be anything. So what I do is basically write this particular thing as real part and I times capital H. So, and my z as x1 plus ix2. So then these downward flow lines are given by this equation, Lambda is the flow parameter along those lines, and this minus sign basically tells you is the steepest descent line. If there is a plus over there, so that will give you a steepest ascent line. So the one with the negative sign are the ones which are timbals. And Gij could be any Riemannian metric on the complex plane. Depending on the problem that we are considering, one can actually properly define it or customize your Gij in a way. This function, this little h, is also called a Morse function. And so if you look at the behavior of the Morse function along the flow lines, steepest descent lines, so if you just compute dh by d lambda and plug the things, you will see that it is less than equal to 0. So the behavior of h along the flow lines is decreasing. So if you plot e to the power h as a function of the flow parameter, then it is basically like this kind of a inverted bell curve, so the bell curve that you will see. So this picture is taken from this earlier article by Lenners, and so there he has a very nice explanation for this kind of a thing. Let's choose particular G. So we choose G to be something like this. So it allows us to like analyze the behavior of capital H also. Now, if you choose this particular G, then if you compute the behavior of capital H, you will see that capital H actually is constant along the flow lines. Both along the steepest descent and ascent lines, it remains constant. It's a simple thing, it's a line of constant phase, but it helps us numerically do the calculation much more strongly. Because in numerics, like we don't have a very good handle of always dealing with differential equations, so these kind of functions help us in basically just plotting it much more nicely and getting a grasp of what is happening. So then, okay, so the oscillatory integral, they become convergent along the timbals. And this motivates us to check whether if it is possible to deform the original contour that we had into something which is a summation of all, so integration done along all the timbals. If we can find a way to do this, then that is basically a kind of a generalization of weak rotation. So the original integration contour, whatever we have, suppose you have from 0 to infinity, the original integration contour is like that. So if that can be like written as something like a deformed integration along the set of integration done on the timbals, you may have more than one timbals that you have to take into account. So that's why we have a summation. So if you do if you can show this thing is there, then basically that's a generalization of the weak rotation. So in this thing, there is a very subtle way to choose n sigma, which I will not talk.
Sorry, just a quick question. Is there any formal difference between this and the standard 200-year-old method of steepest descent for integrals? Is it just that this is higher dimensional? Or?
I think it's just we are doing it in complex, basically. I think the method is just the same. Yeah.
So I didn't understand the answer. I thought the point was this is telling us how to do the steepest descent. So which saddle points you should pick and so on. So I thought this is the formal proof for
we will
how
come
to
there.
correct.
We'll come there. So
That's not correct? What
yeah, so we'll come to the saddle point also and other things associated, how to pick up the relevant and all that. And the way to pick up the correct timbals. So there are multiple timbals, only some of them contributes actually.
But isn't the answer to Steve's question that if I just did some naive saddle point analysis, I might not know how to pick up the right saddle points, and this tells us how to do it?
Yeah, but the
what
question
contour I
is,
should go on?
I guess the question is the steepest descent, which is not the same as just the saddle point contributions. You're looking for the steepest descent, and that's also in the complex plane. So the question of Steve's is, how does this differ from the ordinary thing where you do look at the steepest descent curve, and that's what you're picking up. And that's the, like you said, 200-year-old
So okay,
technique.
in this case, like what happens, like you will have multiple saddle points. So what happens, and some of them may not contribute, and only some will contribute. So in the original, probably the long back, so all of them like basically contributes. In this case, like if you have, suppose you have 4 saddle points, in the end only 2 will contribute, which will become your relevant ones. But if you do it like in the other case, like you will, all of them will be equally like contributing. Yeah. Definition of steepest descent is basically the same. Like it was the same before also, same now also. It's just the way of picking the relevant saddle point that will be, yeah.
I think, Gaurav, just one small thing. I thought that your function, then when you look at the flow equations, the function should be a Morse function, so the eigenvalues come in pair, I mean the positive and negative, and then
yeah,
so
yeah.
The choice of G also is
choice of G has
it's
some
like
role.
choice of polarization.
Yeah.
And also just one small question. So these J's, I mean in general,
So J's are basically just a name for the Timbals.
Yeah, but I think you may have force. I mean, they should be linearly independent in some. I mean, you can have n symbols, but
right.
they are not linearly independent in the sense of a homology argument. Like you have to take a subset which forms a basis, right? I thought that was also. Maybe I can ask you later.
Okay. So basically, like the necessary condition for picking up the timbal which is relevant and is to look at the behavior of steepest ascent curve from, starting from that saddle point. If that steepest ascent curve intersects your original integration contour, then that saddle becomes the relevant saddle. And the integration has to be done along the timbals which is passing through that saddle. So those are basically the new deformed integration contour that will constitute, which are associated with the relevant saddles, which are like this. You have to see the steepest ascent curve starting from that saddle point. If it intersects your original integration contour, then that saddle point will become relevant, and the timbals associated with that saddle point, they will become basically the new deformed integration contour. And there will be many of them. Sometimes, like in some problem, depending on the boundary condition, only one will be there. Sometimes, depending on the boundary condition, there will be two or more. So all the timbals will be contributing, but all of them will come with a phase. The phase part I am not discussing, it's a little bit more tricky. So the phase part is there. And there's another one, which is this n sigma that has to be, because different orientation along the flow lines and how it aligns with the original integration contour. So either you get a +1, -1, or 0.
The G Z bar thing that you had, that choice of metric, it seemed a little arbitrary. Was it?
Yeah.
Is it arbitrary or?
We just, that is just for an example, just to show that, okay, just to understand the behavior of capital H. But like depending on the problem, like we can have the freedom to choose.
So there is some freedom in choosing.
Yeah, so as long as it is Riemannian on the...
But the fact that the phase was constant on the thing, does that depend on the choice of G or no?
Yeah, that doesn't depend on G. So that is just for simplicity to show it.
Thanks.
Look, Renata wants to say something.
Yeah, so who tells me that this is a physically sensible way of choosing a contour?
Okay, so so the thing is, the way that I decide is like we in the end. So I want something like the bell curve again, and if at the saddle point e to the power h that we are looking at, so if h is negative, then basically along the bell curve it will be further and further negative. So that like if you do the integration along this thing, it will be bounded. Now, how to find what are the saddle points which are referring to H negative? So that comes out basically by this condition and this thing. So if you like look at the behavior of steepest ascent, so if S is a real function on the real line, then H is 0 at the real line. If you trace back along the steepest ascent curve, along the this thing, so H will become more and more negative, and it will become negative at the saddle point. So basically that saddle point will become relevant.
I'm just thinking, of old work, we're talking 1980s, like, Halliwell, Hartle, of course, people, these are very simple models, right? So as long as you work with the simplest cosmological models, it's more or less clear maybe where you want to end up. Maybe now you have more varieties and you can talk about, I'm integrating over Lorentzian and Euclidean and what have you. But people just played around with various ways of deforming contours and looking for some conditions, right, physicality, sorry, physicality conditions to pick out one of the many choices. So what's essentially new in this game?
So, so one, like we started with the this oscillatory thing, and we don't know whether that will be just the naive integration of that oscillatory function is convergent or not. Now I want to cast that into something which is a Gaussian integration. So now if I want to do that, basically I have to rely on the nature of what are the saddle points and what is the Morse function behavior along those saddle points. Now, some of them saddle points will have a Morse function which is positive, and only few of them will be having a negative one. So only the ones, so that is another thing. So it may happen, so the saddle point will have a negative Morse function, but the steepest ascent curve starting from it may not intersect your original integration contour. In that sense, like it doesn't contribute at all. So that is another criteria that helps us in picking up. And then like basically I want that the integration should be convergent. So that's why I basically just pick up only those saddle points for which H is negative, and those ones which intersects the original domain of integrations.
So let me turn the question around. So say, we have, can you phrase it the other way around? So you have a list of, physical problems you want to address, the conformal factor problem is, of course, a key one here.
Yeah.
And you say, okay, I want my analytic continuation to do this and this and this and this, and this is the unique answer. That's how people asked in the old days, because of course you want to generalize this also as a method. As long as it's just a single scale factor. I mean, there are many ways of arguing your way to get there.
Maybe take this to the longer discussion, and Alok has
I need to think a little bit about this. So this one, okay, yeah.
Sorry, just wanted to, no,
so mathematically, it seems like kind of a unique way of picking it up. But physical, that one, okay, I need to think a little bit.
I just wanted to answer to Chetan, just one comment I wanted to make, that the choice of G is, if you think of this as a Hamiltonian path integral, so your phase space, and then choice of G, if you give me a G, is same as you give me, because we have a symplectic structure, that's same as you give me a complex structure. So choice of G is same as polarization. It's exactly the same.
So basically, so you have the original integration contour, which basically becomes a summation of integration done along timbals. And the integration on the timbals is basically just bounded and finite. So let's come to the mini superspace. So let's come to the mini superspace. So basically, we just have now a FRW metric. So we have 2 degrees of freedom, which is scale factor and this lapse. Now, there are like 2 dynamics basically, which 2 of them will play a role. There's still some diffeomorphism invariance left around, which is time reparameterization. And so the range of coordinate for T is basically 0 to 1. We fix a gauge also here by choosing n prime equal to 0, which implies basically n will be constant. So the original path integral of the gravity will ultimately be reduced to something like this. So the integration over the scale factor and an integration over the lapse. So here we have already performed the other integration, which is the integration over the ghost and other gauge other freedoms that we had. So ultimately in the end, basically we are left with this thing. And this is what we have to analyze for the various boundary conditions and to see whether we can get something out of it. So people have studied Einstein-Hilbert part already quite a bit, and some part was already known, some part is not known. So what me and my students have been doing for the largest thing, we added this extra term over here and to see what additional does it give. So it just has 2 time derivatives. It's a topological term in 4 dimensions. So it's expected to not play any role in the dynamics. But on the boundary, and if you look at the path integral of it, which we are able to compute it exactly, we'll show in the talk that this term actually helps us in dictating and picking up the right boundary conditions. So that is basically our recent work, where we showed that actually the no boundary proposal or the boundary condition corresponding to the no boundary proposal are the ones which are giving dominant contribution in the path integral. So rest of the talk is basically just mathematical techniques of doing the calculation. Yes?
Gaurav, do you fix the sign of alpha?
I have taken to be positive.
You have taken to be positive?
Yes.
Okay.
So to do the calculation much more like a thing, so if you have the original integration variables, which in terms of a and n, so if you write the gravity action in terms of a and n, it has some weird kind, so yeah, cubic terms are there, but that thing can be recast by doing some rescaling of parameters, and ultimately the full path gravitational action basically becomes like a quadratic thing. So you have something as a linear in Q, there's a kinetic term, there's this and this. So the Gauss-Bonnet term appear right only as a total derivative over here. So then basically we just have to work around with the path integral in the language of Q and N. So some work has been done in the past. So people have studied this particular same thing by Lerner. And they found that if we impose Dirichlet boundary condition at t equal to 0, and of course Dirichlet boundary condition at final time also, then the system, I mean, although it gives the correct exponential powers, and but there are issues. The perturbations are not suppressed. As a result, this was a bit demotivating, and they decided to look at the Neumann and Robin. And that is where they noticed actually the perturbations are suppressed, and the prefactor is coming out to be exactly the same what Hartley-Hawken also saw long before in the 80s when they were studying the path integral in the Euclidean setting. They also noticed that there is a transition, let's not call it transition, there's a signature change. The signature change happens from Euclidean to Lorentzian as the size of the universe becomes larger and larger. So more details on this you can in the review article. So yeah.
One quick question. The previous slide, the first bullet point. So what was the difference between the two calculations? So the first one was defined in Euclidean signature.
In the Lorentzian, so okay, the difference is, okay, so Hartley-Hawken found some sign, okay, it was some sign e to the power some coefficient. So I think it came with plus, and these guys, they found with a minus, basically.
No, that's the result, but I'm asking what was the difference in the setup? In the setup of the two?
Yeah, okay, this is just Lorentzian, basically, and they do it with these techniques.
So yeah, I also I didn't understand something about boundary conditions. In the Euclidean case, there is no boundary. So what does it mean, Dirichlet versus Neumann versus Robin?
Basically, what Q is equal to 0 at t equal to 0. So no boundary, like, so if you just bluntly put that Q is equal to 0 at t equal to 0, the model, everything you can do it, but when you study the perturbations with this configuration, the perturbations will have an exponentially growing behavior in the path integral.
I thought you're doing the integral on the Euclidean hemisphere. You can say
that
you
is,
can write the hemisphere in
yeah.
some coordinates and say q equal to 0, but really the hemisphere is well defined without putting any boundary conditions. So what does this mean?
That is in a later part. So that came a little bit late. So like initially they did not have the Euclidean one. So when you had only for the Neumann and Robin only, then you saw that there was a Euclidean. This thing was there, the Euclidean cap in this thing.
I thought the Hartle-Hawking was the hemisphere. That was
right,
the proposal.
right. The Hartle-Hawken is the hemisphere only. So the Euclidean cap, you remove the singularity by a Euclidean cap.
Does the Hartle-Hawking Euclidean way of doing the Euclidean path integral have an equivalent as a contour in the Lorentzian, and it's just not the Lefschetz-Stempel contour? Question mark? Does it?
Not checked yet.
Okay. Yes. Okay, thanks.
Thank you.
Yes, what Turok and his collaborators argued is that there are choices of contours, and one of them gives the usual Hartle-Hawking wave function, but that it's not the one that's picked out by Picard-Lefschetz theory.
I see.
That Picard-Lefschetz picks out something equivalent to the Vilenkin boundary conditions.
So this is what he is saying. This is the one that basically is this one, where the perturbations are also not suppressed. But if you go to by defining Neumann and Robin boundary condition at initial time, which is basically replacing the this thing singularity thing by your the Euclidean cap, then basically you get the right kind of exponential prefactor as in the Hartley-Hawkins case, but also the perturbations are also well behaved. So just,
Yeah, yeah, yeah.
I think the point in that sense is that initially Hartle and Hawking were using the wrong contour. Is that the answer? Is that the reason why it is, it's, you know, they got a different answer? Because if it can be analytically continued, I don't understand what it means to say that, you know, the two answers are different.
No.
That's what I would have thought too, but I thought the answer was that it does, I thought. No? Huh? That's what Steve said.
Respond.
So that's why I'm confused.
Maybe Gaurav can answer.
So there are quite a bit of slides. Maybe that is a good answer that I can give right now.
I think you continue. There is 1 hour for discussion. So.
But I think this can continue on to the discussion.
We're going to have a lot of discussions about this for sure, because this is actually very interesting, confusing, and so on. So, yeah. To many of us, confusing, but clearly not to Gaurav, so he'll clarify.
Okay, so the actual no boundary, this thing is the path integral is done over regular metrics which are non-singular. The original path integral that was done by Euclidean in the Euclidean Hartley-Hawkins way in the 80s. Now, that is basically with the Euclidean cap in the initial time. Now, if you translate that thing into the current work of Lehner and these guys, they basically is translated into like putting a boundary condition of on initial momentum, which is with -3i. So, and this is the only boundary condition which gives us stable perturbations. So, anything else like the perturbations blow up or they are don't have a good control over it. So, the original no boundary proposal of Hartley-Hawkins translates into a boundary condition which on the initial momentum, which is basically imposing a Neumann boundary condition at t equal to 0. And it's a complex this thing, so imaginary. So, our work, what we show that actually we derived it basically instead of imposing it or borrowing it from this thing, we compute the path integral for generic pi naught or in the Robin case for something generic. Then basically we showed that the leading contribution that comes in is basically only this one that where the integral peaks up. So this is this part of the talk is just telling how to construct the boundary action basically, and we managed to like found something interesting which was not there before. So it's just a process of computing the boundary action. So you vary the action around the background, and you have the collection of boundary terms that are there, and basically I'll go through it quickly just in case if somebody has a question we can deal with it. So if you these are some boundary terms that are there. So you have a momentum which is defined like this. So the boundary terms over here that comes out from the total derivative eventually translates in the language like this one. Now the whole idea of setting up a consistent variational problem is to get rid of these kind of terms either by choosing a sensible boundary condition or by adding a boundary action which basically cancels these contributions when you vary the full action. So that is where we do the thing. So for the Neumann case, if we impose the Neumann boundary condition at t equal to 0, which is basically fixing the momentum and the final size of the universe, it ultimately translates into a surface action which is like this. So the first part is basically your given Hawking term. So this is coming from the Gauss bonnet. So this is for the Neumann boundary condition. So the full total action that eventually comes up is basically something which is a bulk thing, and a boundary pieces that is over here. What happens for the Robin case? Like we imposed that the linear combination of the momentum and the position is fixed. And the final size, of course, is fixed. Now, if you do this thing, you again do the whole algebra, and you get some additional terms in the boundary action. So this term is the same as the Neumann case. This term comes from the Einstein-Hilbert gravity part, and by fixing, imposing Robin case for the Einstein-Hilbert gravity, this part is coming from the Gauss bonnet. So to figure out this part, it took us a bit of time also, because most of the thing that when we use all the results which were already there in the literature and translates into this thing, it basically all of them were giving us a 0 answer. And when we tried to trace back the error, we couldn't find out. So eventually we pinpointed it because it was a derivative method that was missing the constant piece. And that eventually gave this thing correctly. Now, once we have this correct term of the boundary action for the Robin case, everything eventually matched completely decently. And for the Robin case, again, you get the same kind of action, but where the pi is replaced by capital P. Yes.
Yeah, so your previous slide, this Gauss-Bonnet contribution, isn't it just the Euler density? Because in 4th dimension you are in, this is the boundary part contributed.
Yeah. So for that,
so this is just a constant determined by the topology of the boundary, right?
So the mistake that what we were this thing when we took the results directly and you put the FRW. So what we were seeing that this term, we were not getting this term. We were getting basically a 0 answer. And for a long time, we actually were satisfied. Okay, our initial results were the way. So there is a proper derivative way of constructing the boundary term also. So that method also gives you a 0 answer, and both the things were consistent. For a while, we were happy, and then it took us some time to dig out this particular piece.
No, I'm confused why it would be 0, because it's the Euler number of the boundary topology, right? I mean,
yeah, because that is S3.
That is S3. Okay, that's why. Okay.
Gaurav, just a small question. So for
yes.
GR, when alpha was 0, people had done this with these new conditions, or this was also not done?
You mean Einstein-Hilbert part?
Yeah, just without alpha, where alpha was.
Without alpha, people have done, but only at the saddle point level, not the full results were known.
Okay, thank you.
So in the beta going to 0 limit, we get back the Neumann thing. So there's a smooth connection between the two. And let's look at the path integral now. So basically, how much time do we have now? Okay, good. So now basically we just have to worry about the path integral for the Robin case and the Neumann case. And that is just a little bit of technicality that we have presented in the paper, which is in this one. And yeah, so algebraic details probably we will just have to go in that paper. So we have, let's start first with this particular path integral. So we also developed some quantum mechanics in our paper. So that results were not easy to dig out actually. So for the Robin case, we searched and we couldn't find it. So we basically derived everything on our own. And then those results were used to compute the path integral eventually. So the Neumann case, we have this thing. So the Neumann Q integration is actually a little bit simple. And we have just this eventually exponential factor and another exponential factor, which is depending on the lapse. So eventually we have to just do the lapse integration from -infinity to +infinity, which goes like this. Now the thing is, like we can do a little bit of algebraic over here manipulation. If you shift the lapse by this particular constant piece, you can convert this into a product of two functions. So there's a function which is dependent only on the initial boundary, and there's a function which depends only on the final boundary. So the full path integral actually just factorizes into two parts. So we will come to, it's already you can see that this has a structure of a Airy function, but we will come to how to compare. So you have this particular piece and this particular piece. For the Robin case, again, something similar happens. There's a bit of algebra, but again, something similar happens. We used a little bit of a trick over here. So we write the Robin case as a kind of an integral transform of a Neumann case. Because Neumann, we knew the exact results. So the Robin case and the Neumann case, they are connected with each other by this kind of an integral transformation. Now, if you know the exact result over here, all you have to do is just an integral transform here and get the result for the Robin. So this is what we also use in our paper. So if you do the algebra correctly, so basically the full Gauss-Bonnet path integral for the Robin case eventually just factorizes into various pieces. There's a Gauss-Bonnet term that comes in. It's an important prefactor, which we will analyze. Then there's an Einstein-Hilbert part. So this is a complete Einstein-Hilbert part. So there is this phi, this additional function that comes in over here, and the psi2 qf, which was also there in the previous case for the Neumann. Now let's start analyzing with the Airy function. So we have the Airy function definition, we just use it, and we say the Neumann case is just exponential times the Airy function, while the Robin case is a product of two Airy function and these exponential features. This is the exact result. for where I haven't fixed what is P and what is pi yet. And QF, of course, is left also arbitrary. So this is a complete this thing. We analyze which one of the configuration will give us the dominant contribution in the path integral. So to do that, we do the following. So we take the h bar going to 0 limit and see which one survives in the h bar going to 0 limit. To start, we look at the Gauss-Bonnet prefactor. So the Gauss-Bonnet prefactor in both the case is the same, except this is over here, but that will go in, become over here. So the Gauss-Bonnet prefactor is the same for both the part. So we look at this particular function, e to the power I a over h bar. A is basically this particular function. Now in the h bar going to 0 limit, the dominant contribution comes from a prime equal to 0. Now it will basically lead to two initial boundary conditions. So one of the boundary condition, if you take the beta going to 0 limit, actually refers to the Hartley-Hawken. So the green one, I hope you can see the green one. So the green one refers to the Hartley-Hawken, which was originally studied by in the 80s also. The red one refers to the Wellington. If I do the following, if I write my P as I times Y, so basically you are going in a kind of a Euclidean, so you will see that the Hartley-Hawken is in a kind of a valley, and the Wellington is on the top of a hill. We haven't yet analyzed yet this part, whether Wellington is really unstable, although the picture tells us like that the Hartley-Hawken is stable and the Wellington is referring to unstable. But we haven't done the full calculation yet, whether it is really, this picture is really telling us something more. I think the behavior of perturbation needs to be analyzed in this case now, which we haven't done yet. So this h bar going to 0 analysis tells us basically the green configuration that is there is the one referring to the Hartley-Hawken and is referring to the configuration in the valley. We can do the same analysis for the beta. So we have an additional parameter in the Robin case, which is the beta parameter, which you can do the h bar going to 0 analysis for the same thing again. And that will tell us basically beta, there is a configuration referring to beta dominant, which is basically just this thing, and what are the allowed values for this, which are referring to the dominant contribution in the path integral for beta. We define some additional variable and basically just rewrite these exponential factors in terms of those variables. So these exponential factors comes by analyzing the asymptotic limits of these Airy functions, and eventually they become just like exponential this thing. Anyway, so we notice that in the limit 0 and 1, so if x is in the limit 0 and 1, we basically precisely get the Hartley-Hawken state and with a positive weight. So this is the same what was also observed in the 80s of the Hartley-Hawken. The range beyond 1 is basically doesn't exactly produces the Hartley-Hawken, but it still at least gives a positive weight factor. But after a while, it becomes negative. So as you keep on increasing, it becomes negative and eventually goes in the unstable regime. So the Hartley-Hawken, actually the stable state we can call the P equal to minus this thing and X in the range, this particular thing. So this is the only stable values that to further find more finer analysis of this, that we haven't done yet on the study of perturbations. The fluctuation, metric fluctuations, that has to be done to further fine tune this thing. And this is just basically just plotting the Airy function. So, right. So remember when we computed that full calculation, so we have this particular Airy function which appears for both of them, for both Neumann and this thing. So this, if you plot, it basically tells you that as the size of the universe increases, this particular increases first, and then there's an oscillatory feature. We will analyze this with a saddle point approximation and see what it means actually. It has some meaning. Let's do the saddle analysis now. So if you do the saddle analysis in the Neumann case, let's just first understand the Neumann case for the saddle analysis. So if you do the saddle analysis where the size of the universe is greater than 3 over lambda, there are two saddle points are there. Both of them are relevant. The thick black line that you see over here is the original integration contour. This and this are the saddle points which are lying in the complex plane. So they have a real and imaginary part. And so these red lines are the timbals, and these black lines are the steepest ascent lines. So both these steepest ascent line intersect your original integration contour, and both of them become relevant saddle points. So the timbers passing through them basically eventually leads to your deformed integration contour. So the actual integration contour, which is on the black line, eventually becomes the integration done along these red lines. In the saddle approximation, if you work it out, it basically gives you something like this. There's a prefactor. Each of these saddle contribution comes with a phase in front. So this phase has to be properly determined. Minus infinity to plus infinity.
Oh, I was asking that whether the integration contour was from minus infinity to infinity or 0 to infinity.
Minus infinity to plus infinity. We'll come to it. It's a little bit more delicate also.
No, but you write the amplitude there. But if you integrate from minus infinity to infinity, it will be the solution of Wheeler-DeWitt equation, right? This was shown by Halliwell. So I don't.
We'll come there.
Okay, okay.
So yeah, so there is this phase factor that comes in over there, so which has to be properly determined by this saddle analysis, which I don't describe it over here, but you can see in the paper. So what happens for when Q is less than 3 over lambda? So there are again two saddle points, but one of them is irrelevant. So one of them, basically, if you look at the steepest ascent line, so steepest ascent line of this particular does not intersect your original integration contour. Only this one does. So only the timbal passing through that basically is the relevant. So both of them are actually imaginary. This is a Euclidean saddle. So for QF less than 3 over lambda is the Euclidean saddle, which is basically dictating the path integral. And for QF greater than 3 over lambda, there are two complex saddles are there. They both contribute and gives you the oscillatory feature in the path integral. So at Q, this is a degenerate case. So at QF equal to 3 over lambda, there's only one saddle point. Both of them merge together, and basically just this particular timbal is left around. But in the Robin case, one can do the similar analysis, but given that we already showed that the Robin case and the Neumann case were related with each other, so part of the calculation could be avoided, and it helps us in saving some of the work. This was also done by old work by Lehner, where he analyzed directly the Robin path integral in the Picard-Lifshitz manner. So he obtained 4 saddle points, and he showed eventually 2 of them were irrelevant. In this style of doing, we were able to show that the 2 relevant saddle points of the Neumann case, they were already there, but in this style of doing, it will tell you basically only one of them survives, and only one saddle point is the one which is relevant. So that actually helps us in figuring out that which one is relevant and which one is not. So we do the same kind of analysis again. We write the integral in this particular manner. We have some particular exponential function in the front. And in this, there's a Morse function corresponding to this particular thing, and we basically look for the saddle points, saddle configurations. Only one of them is P referring to minus 3i is the one which does not move around if you vary x, and this remains stable. Other saddle point actually keeps on changing its behavior. So this analysis basically just tells you which one of them was the stable and which one of them was not the stable one. And basically just give you the picture for the stable configuration and the allowed region where the Hartley-Hawken was there. So there are 2 stable points, there are 2 saddle points. One of them is not stable, and this one is the one which refers to the Hartley-Hawken stable saddle point. And if you basically then you have to just perform the saddle approximation of the Picard-Lifshitz, and you get the final answer. Let's summarize what we have done so far. So we start to study the path integral in the Lorentzian signature, and it's a reduced setup. It involves mini superspace approximation where we investigate the nature of the boundaries. So we analyzed NBC and RBC case and keeping DBC at the final boundary. So we were able to compute the path integral in this simple setting exactly, and that helped us in analyzing and figuring out basically which boundary condition was favored and which one is not. And we were able we can say, we kind of derived the boundary condition which was giving dominant contribution to the path integral. And it actually turns out that that boundary condition was the same as the one that was studied by Hartley-Hawken back in the 80s, which is basically replacing the singular part of the universe by a Euclidean cap. So, but this result we were able to see in the presence of Gauss bonnet. If the Gauss bonnet is not there, we cannot see this thing. Both Hartley-Hawken and Wellington are equally good over there. We have to go to another level to see that particular, which one might be favorable, which might. So both, you can always construct your universe in a way that both of them are equally favorable. But if you have a Gauss-Bonnet term with a positive coupling, only the one which was referring to Hartley-Hawken, that boundary condition was lying in the valley. The other one lies on the top of a hill. So there was a signature change event that happens, which goes from Euclidean to Lorentzian. But this is, was also observed by earlier works of Lehner also. This is just for completeness. So Picard-Lifshitz analysis helps us in verifying our exact results also. It gives us a better understanding of what was the exact results was showing to us. And this study highlights the importance of Gauss-Bonnet term, which usually we ignore, but because it doesn't play any role in the usual dynamics. But in this case, it has a role to play also. So there's some the work that we are trying to understand the behavior of fluctuations and how that will be, because that is needed to figure out which boundary condition will be more stable. Matter field, which we are still doing, and analysis of a more complicated geometry that is not very well understood yet. Higher derivative theories, we started some time back, then it became too complicated and we just took a pause and went to something else. So connection with other phenomenological issues, that is a more longer term goal. So Sumanto and his student are studying the same kind of path integral, but including torsion into account also. And maybe we will hear from them sometime in future. So yeah.
Okay, let's go.
Yeah, so Gaurav, I have a couple of questions. So I still don't understand the Gauss-Bonnet contribution.
Yes.
So without the Gauss-Bonnet part also I have a Hawking-Hartle.
You will have, but you will also have Wellington also. Both of them will be there and you cannot distinguish which one of them is lying in the valley, which one of them in the top of the hill.
Okay.
So with the Gauss-Bonnet, we can, yeah. So this is your Gauss-Bonnet contribution. So if alpha is 0, so this term is not there. Okay. So both of them basically will be equally good, and you can construct your theories in both ways actually. So, but then if alpha is there with a positive sign, and then basically you can see that, yeah, this one is
this one is the stable one.
Yeah.
Okay, okay. Now, so alpha has to be positive.
It could be metastable also. That is another thing. Because if you take the full limit, it can tunnel and just again decay. So that we haven't done yet.
So alpha is stable.
Yeah.
Alpha has to be positive for this.
Yeah.
So alpha introduces a length scale. Does it mean that there is a minimum size of the universe from which the universe is coming out, or?
Oh, this okay. We haven't analyzed yet. But
okay.
Yeah.
Okay, I can talk to you later. Okay.
First question is just. I also have a couple of clarification and a question. Clarification is, did I understand correctly what you were calling Dirichlet boundary conditions meant you imposed that the size of the universe, scale factor is 0 at t equal to 0. So it was really a singular starting point. And what you're calling in Neumann and Robin, there was no singularity at the starting point. So is this correct, what I said, or not?
Kind of, yes. So in a Neumann and Robin case, we don't put a condition on the size of the universe, right, but on the momentum, and a combination of momentum and the position.
Right. So it's not singular in particular.
Yeah.
I see. So what you're calling Dirichlet is really quite different in philosophy from Hartle and Hawking, because you were really examining something that started from a singularity. The next question I have is about the correctness of this approach in principle. For Hartle-Hawking, one thing one could check is, let's say you took a quantum field theory without gravity in de Sitter space. Then doing this Euclidean path integral on the hemisphere would generate for you the correct Bunch-Davies vacuum. It would generate for you what we call the Euclidean vacuum. Let's say I apply this procedure, I forget about gravity, just to a free field theory, propagating in de Sitter space. Will we get the correct Euclidean vacuum wave functional?
Honestly, I don't know yet, so I have to check it. But yeah, I haven't.
This work.
I mean, the no boundary proposal was motivated by saying that that's the correct vacuum. Because, no boundary integrals do give you the vacuum, which you can just check without gravity, where there's no conformal mode problem. Just take a scalar field and do the no boundary path integral. It gives you the Euclidean vacuum. So the question is, if there is other Lorentzian prescriptions, do they work at least when gravity is not absent? I mean, that was the motivation for the Hartle-Hawking paper, right?
Yeah. Yeah, so I have this more or less same question. So where do you impose your boundary condition? It is of initial state or final state?
Both actually. So in the
Both.
final state, we are imposing just the size of the universe is fixed. So at the initial state, we are playing around. So which one of them will be the one which will give
and in the both Dirichlet and Newman, in the both case you are imposing.
No, the final
condition.
is Dirichlet. So initial one, initially people studied Dirichlet, it gives an unstable universe. The perturbations were not suppressed over there. Then people also studied Neumann and Robin. There the perturbations are suppressed and well behaved. That was analyzed also previously. But then the full, we just basically do a better full analysis to figure out the effect of the Gauss bonnet and which one to see, yeah.
And do you have any comment of how to take any comment on the classical limit of this? And so how do you take the classical limit of your, all this, what you are doing?
Yeah, well.
So, because this classical limit is exactly related to how you impose your boundary condition. If you include gravity,
yeah.
So the Dirichlet boundary condition will give you the no radiation condition, but if you impose Neumann, then it will give you radiation.
Okay.
So do you have any comment on that? What is the limit of the classical thing of your all this analysis?
Not analyzed yet, so as of now, yeah.
Just one small question. You had a plot with where QF was larger than something and two saddles. There were two saddles in the.
Yeah.
So the interpretation that classically you can have two possible.
Yeah. So both these saddle points are equally.
And Lorentzian.
Yeah.
Both are Lorentzian.
Yeah, both are. They have a real and imaginary part also. So there is not completely Lorentzian. It's not lying on the this thing.
So complex geometries.
Yeah, complex geometries.
Okay. Thank you.
Can I ask? Yeah. So I just wanted to understand the original, so when you say no boundary proposal, do you mean that at the initial, there is a Q equal to 0 or A equal to 0 starting point, or is that the only one that you mean by no boundary, or do you mean that it can also be
replacement by a Euclidean cap?
Right. So
that is like the actual no boundary.
So there are the initial conditions that you're imposing are either when it is when you're setting A equal to 0, you call it Dirichlet. Is that correct?
Yes.
And when it is
replaced by a Euclidean cap, that we call it no boundary.
No. I'm confused about. So where are you? So A equal to 0 is imposed where? Sorry. No, Lorentzian version is fine. I'm confused about So the initial condition, there are three choices of initial condition that you're imposing, right?
Yeah.
One is the A equal to 0.
Yeah.
And one is presumably the canonical conjugate, which you're calling Neumann. And then there is some linear combination.
So in these last
but I would have thought that the initial, the Lorentzian section, etc., that part comes up. In the initial stage, you're just writing down as a general, the metric doesn't have a signature yet. This is what I would have thought, right? I mean, you're basically integrating over every possible configuration, and then you're choosing the contour that you want to pick, and that's what you call either Euclidean or Lorentzian. And when you say that it basically at some stage it becomes Lorentzian, you're starting with, your contour is basically, becoming, let's say, Lorentzian, real at some point. Isn't that what you mean?
Not very.
I think, no, but I can. I can draw a picture, maybe it'll become clearer. Because I think at the initial stage when you write it, I'm not seeing where the signature is going in.
There are quite a few things are getting mixed up. So probably the graph that I showed you earlier, so that is basically just the behavior of G, the full path integral as a function of the size of the universe.
This discussion maybe we can take in the discussion session. Is that okay? Because we will come back in few minutes. So Renata.
Yeah, just a couple of comments. So I think you have this new way of thinking about these contours. I think by all means it should be investigated, what it means and also what some of the physical implications are. But number one, I still see, inevitably there will be there are choices involved, and then you better look for good physical reasons for why you make those choices. So I would say in the old days, the problem was not so much finding any old prescription that whatever you want to have well-defined, the wave functions of the universe or certain convergence properties, to find something, but to find something that is more generally valid. So for more, you mentioned it, for more complicated cosmological models, do you have any indication how this works? But of course, eventually, if you like, for full quantum gravity.
Yeah, so
right?
that
Because
is,
as long as I'm just playing around essentially with a single variable, I can do very many things.
This one is too simple. Currently we are playing around with a little bit more complicated, because in 3 dimension you have much more geometries that are there, which are can become, and the very, very small scale, all of them can become equally important, or at least some of them will be. So that is the idea that we are actually going after, but the calculation is just becoming a bit more hard. So this one was easy to keep a track of.
So how do you go beyond Friedman? I mean, of course, I don't know, Bianchi models and stuff.
So yeah, the Bianchi thing that we are doing, and something called KS spacetime, Kantorovsky-Sachs spacetime. So that is currently we are working on.
Okay.
And these are not the only 2 geometries. There are much more, because in 3 dimension you have a classification of there are 8 geometries are there, so which are basically So that is the idea, main idea basically, to study all of them. But this one was So currently KS and Bianchi is a little next stage. That to keep a track on how complicated. So I don't think we can do exact calculation.
Whether it's doable at all is also part of the question.
So far, there are technical hurdles already we were facing over there. There's a nice way of performing these path integrals, which we can do analytically exactly. That we are not able to so far achieve yet. So there's a lot of mixed terms are there. We are not able to disentangle them and write it in a way.
Yeah, one final remark, as someone who works on quantum gravity, of course, the idea in principle should be, these ambiguities should be fixed coming from a full theory of quantum gravity.
Yeah.
So I just want to mention, from our lattice calculations in 4 dimensions, what emerges naturally is the Vilenkin wave function.
Vilenkin one.
Yeah, and there's a non-perturbative mechanism that you see over here that comes actually from the measure, the path integral measure, that does something to the overall sign of the kinetic term.
Exactly. So so here we studied for alpha positive. So this we noticed that if I change the sign of alpha, then basically this one becomes in the valley and this one becomes the top of a hill.
The thing is with us, this is dynamically generated, so you're not putting it in by hand. So I'm just mentioning it as a reference point.
I see.
Yeah.
Okay, thank you all. So let's thank Gaurav.
Oh, you give it to him. It's okay, call him. Okay. We are going to switch things around just a little. As I said, we have a fantastic team behind this whole week, months, that's put together this entire conference. And they've worked so much behind the scenes. You've seen a couple of them, but there are others, and we really want to give them our heartiest thanks. You can't sit that way because you're going to have to come out and get your, you're going to have to come to the front. So let me, let me just, and Madhavan, Madhavan, you two, you can just sort of together together, thank them, and yeah. Oh yeah, come sit in front. Please sit in front. And yeah, they have to also come. Yeah. And please sit in front. Now, okay. Okay, I think we forgot one bag. Okay. All right. So, Manju has been at RRI for much longer than me. When I first came to RRI, he was basically looked after, every little thing. Do you need to get this done? Do you need to get that done? And Manju's been my friend for the last 20 years. And he's, he retired a few years ago. But of course, when we had to organize this conference, we were like, how are we going to do this without Manju? So we requested him to come back, and he very, very kindly agreed. Last few months have been difficult for him because he had to get back into the office mode, learn new things, learn how to deal with Google Sheets, learn to deal with my temper, my frustration. And so I'm incredibly grateful to Manju for being here, making this meeting a possibility. So thank you very much, Manju. It's actually emotional. So, and Gayatri, who became our TP secretary right after Manju left, but then she was so good at her job that was sucked into the rest of the institute, and we would meet her every now and then and say how we missed her. But she as well came back to help us, and she and Manju have been an incredible team, working together, putting the whole conference together, as you've all noticed. I want to please ask her to come up here. And she's taken time off from a family function to be here with us today. Thank you so much. Thanks a lot. Really. So now I'm going to go through the list of other people who, of course, have been very, very important. Sachin, who is there, who's again been coordinating a bunch of things. One of the most efficient people. You need something done, he's out there, he's done it already before you've even thought about it. So please come up, Sachin, and I can't tell the difference between the different, so please help me here. The different colored things. Yes, please. Thank you so much, Sachin. Thank you. Then we had Ritik and Anjali, please come up. So they've been helping with the website, posters, the photograph we had on the lawns. Thank you so much. Thanks. Then we've had, so I should also, before I go on to anyone else, I should thank Mahadeva. Where is Mahadeva? There, Mahadeva is a very important person in TP. Whenever we need anything, he's from the theoretical physics group, so he's always there to help you with anything. Those of you who have needed keys and things for your offices this week, you know him well. And he's been around as well, so many of you who have visited will know Mahadev. So thank you so much, Mahadev. And of course, the reason this is working, the reason that worked, I don't know how to work it, Madhavan doesn't know how to work it. And so we really want to thank the fantastic team that's been out here helping us with the hall. So let me just read their names. Arun Sairam. Thank you so much. Fanindra. Yes, thank you, thanks. And Ranjit, of course. Where is he here? Thanks. Thank you. We also have Sundaresh, who was also behind the logistics, took people up and down, in the car, wherever they needed to. Thank you so much, Sundaresh. Thanks. And finally, Naveen. Who has been, Naveen is coming, who has been serving you coconut water, all of teas, everything. So, and thanks a lot. Thank you. Thanks a lot. There are many others, but we're not going to, they're not with us right now, but let me just read out their names. And I hope I forgot my glasses, of course. So. From transport, there's Manjunath P., who did the vehicle arrangements. From library, because all the beautiful things the little abstract booklet was produced by them within a day. I think those of you who hadn't submitted, we even got a rough copy of it to tell people, hey, your name is not in there, just please submit. So that's thanks to Manjunath Pujar. And Munishwaran from the Electric Works, who's managed to make sure that we have we can charge our laptops. Suma, secretarial assistance. And we also have our caterer, Mr. Pasha. The cabs were Anil. So thank you all. And thank you very much. And let's give them a big round of applause.